All things that you see, which are part of the divine universe, will be consumed by fire and will return to their ancient form. This is an appointed change in the universe. All things that are made and destroyed are but part of one eternal breath.
Have you ever looked at the universe and wondered why everything seems so perfectly in place? From the precise orbits of planets to the delicate balance of forces holding galaxies together, it's as if the universe is finely tuned for existence. But is this perfection just a cosmic coincidence, or is there something deeper behind it? Scientists and philosophers alike have questioned why the universe appears so orderly and exact. In this documentary, we'll explore the mysteries behind this cosmic harmony and ask, why is the universe so perfect? And what does that mean for us? Goldilocks principle. The Goldilocks principle refers to the delicate balance required for conditions to be just right for life. Like the story of Goldilocks, where the porridge wasn't too hot or too cold, but just right. In the context of space, it specifically applies to the habitable zone around a star, a region where a planet could maintain temperatures that allow liquid water to exist on its surface. Liquid water is essential because, as far as we know, it's a fundamental requirement for life. If a planet is too close to its star, any water would likely evaporate, and if it's too far, water would freeze solid. But in the Goldilocks zone, a planet can potentially support oceans, rivers, and lakes, which in turn create a stable environment where life could emerge and evolve. Our Earth is the perfect example of a planet sitting comfortably within the Goldilocks zone of our Sun. At a distance of about 93 million miles, Earth lies at just the right spot to avoid extremes. This distance allows Earth to maintain average temperatures that are neither scalding hot nor permanently frozen, striking a balance that's ideal for water to remain liquid. This positioning plays a huge role in why Earth's climate is stable enough to support a wide diversity of ecosystems, from the dense rainforests and grasslands to the deserts and polar regions. If Earth were even slightly closer to the Sun, it might experience a runaway greenhouse effect, like Venus, where intense heat prevents liquid water from existing on the surface. A little farther out, and Earth could resemble Mars, which is cold and arid with very limited surface water. The importance of the Goldilocks zone doesn't stop at temperature. Liquid water isn't just essential for cooling or heating. It's a unique solvent that allows for the complex biochemical reactions that are the foundation of life. Water dissolves a variety of substances and acts as a medium where molecules can move, meet, and interact, forming the building blocks of life. In our cells, water facilitates countless reactions that are critical to life processes, from energy production to DNA replication. It also helps maintain cell structure and provides a stable environment for proteins and enzymes to function. Without water, these intricate systems would either freeze in place or break apart, unable to sustain any complex life. Beyond Earth, scientists are keenly searching for planets orbiting other stars within their own Goldilocks zones. These exoplanets, as they're called, hold promise in the ongoing search for extraterrestrial life. When astronomers look at distant star systems, one of the first things they check is whether a planet lies within this habitable zone. The presence of liquid water is so crucial that it's often the first benchmark for determining whether a planet could support life as we know it. This principle has led scientists to identify thousands of potentially habitable planets, some of which may have conditions that are surprisingly Earth-like. Observations from telescopes and space probes now give us detailed information about planets that orbit their stars in regions where liquid water might exist. But the Goldilocks principle goes beyond just finding a planet at the right distance. Stellar types and stability are also critical. Not all stars are suitable hosts for life-bearing planets. For example, large stars burn hotter and more intensely, with habitable zones much farther out but shorter-lived, meaning any planets within those zones would likely have too little time for life to evolve before the star burned out. Smaller stars, like red dwarfs, have closer habitable zones, but these stars can be highly active, emitting flares that could strip atmospheres from nearby planets, making them hostile to life. Our Sun, in this context, is a kind of just-right star itself. It's a middle-aged, relatively stable G-type star that doesn't produce extreme flares and has been shining consistently for billions of years. This stability allows planets within its habitable zone to experience long periods of relatively stable conditions, providing a steady environment where complex life could arise and evolve over eons. Earth's position in the Goldilocks zone, coupled with the stability of our Sun, has allowed life to flourish in an unbroken chain from the simplest single-celled organisms to the complex and diverse ecosystems we see today. Another factor that makes Earth's positioning in the Goldilocks zone even more remarkable is the planet's atmosphere. Earth's atmosphere acts as an insulating blanket, trapping some of the Sun's heat and distributing it around the planet. This prevents drastic temperature fluctuations between day and night, which would otherwise be more extreme. The presence of an atmosphere also allows for weather patterns, the water cycle, and protection from harmful solar and cosmic radiation, all of which support the diversity of life on Earth. The atmosphere is rich in nitrogen and oxygen, but it also contains carbon dioxide, which plays a vital role in regulating temperatures through the greenhouse effect. It's a perfect example of how multiple factors align to create conditions just right for life. Water's availability on Earth is another factor that speaks to the Goldilocks principle. Earth's position allows for liquid water to exist on the surface, but it's the abundance of this water that has been so crucial. Unlike planets like Mars, where surface water is rare and mostly locked in ice, Earth has oceans that cover over 70% of its surface. These oceans not only support marine ecosystems but also play a critical role in regulating Earth's climate by absorbing heat and redistributing it through ocean currents. Water vapor in the atmosphere contributes to the planet's temperature regulation, while precipitation and runoff continually replenish fresh water for terrestrial life forms. The Goldilocks principle, as seen through Earth's example, underscores just how specific and delicate the requirements are for a planet to support complex life. Earth sits at the right distance from the Sun, orbits a stable star, has a protective atmosphere, and is rich in water, all of which have enabled life to not only exist, but to thrive and diversify into the countless forms we see today. This delicate balance of conditions is why scientists are so interested in identifying similar conditions on planets beyond our solar system. If another planet were to have conditions as finely tuned as Earth's, it could be a candidate for life, and might even host ecosystems that are entirely unique to that world. Now let's talk about these things in more detail. Earth-Sun distance, the perfect separation for life. The distance between Earth and the Sun, approximately 93 million miles, or 150 million kilometers, is not just a coincidence. It's one of the most crucial factors in maintaining a stable environment that can support life as we know it. This specific distance ensures that Earth receives a stable and consistent flow of solar energy, which fuels nearly every process on the planet, from the regulation of climate to the initiation of photosynthesis in plants. Solar energy distribution at this distance is what keeps Earth's temperatures within a range that allows liquid water to exist, making it a habitable world for a wide variety of life forms. The amount of solar energy Earth receives from the Sun, often referred to as the solar constant, is finely balanced. This energy reaches Earth in the form of sunlight, which not only warms the planet, but also provides the essential energy needed by plants to carry out photosynthesis. During photosynthesis, plants use sunlight to convert carbon dioxide and water into glucose and oxygen, producing the oxygen that fills our atmosphere and forming the base of the food chain that sustains nearly all life. Without this steady and dependable flow of solar energy, photosynthesis could not occur, and the intricate web of life that relies on it would collapse. Beyond its role in photosynthesis, Solar energy distribution is fundamental in regulating Earth's climate. The energy from the Sun drives atmospheric and oceanic circulation patterns, creating winds and ocean currents that help distribute heat around the globe. This distribution ensures that equatorial regions, which receive more direct sunlight, do not overheat, while polar regions, which receive less sunlight, do not become inhospitably cold. These processes maintain a balance that keeps Earth's climate within a stable range, allowing ecosystems to thrive and providing a consistent environment where species can adapt and evolve over time. But what would happen if Earth's distance from the Sun changed? Even a relatively small shift in our position could have dramatic and potentially catastrophic consequences. If Earth moved closer to the Sun, even by a few million miles, the increased solar energy would lead to significantly higher temperatures. In this scenario, Earth could experience a runaway greenhouse effect, similar to what scientists believe occurred on Venus. As Earth's temperature rises, more water from oceans, lakes, and rivers would evaporate, releasing large amounts of water vapor into the atmosphere. Water vapor is a potent greenhouse gas, meaning it traps heat from the Sun, further warming the planet. This positive feedback loop could cause temperatures to spiral out of control, turning Earth into an incredibly hot, dry, and hostile environment, unable to support life as we know it. In this runaway greenhouse effect, oceans would eventually evaporate completely, and any remaining water would be trapped in the atmosphere or lost to space. The surface would be scorched by the relentless solar radiation, and the atmosphere would become thick with greenhouse gases like carbon dioxide and water vapor. This is exactly what we observe on Venus, a planet similar in size to Earth, but closer to the Sun. Venus's proximity to the Sun means it experiences an intense greenhouse effect that has led to surface temperatures over 860 degrees Fahrenheit, 460 degrees Celsius, hot enough to melt lead. Its atmosphere is primarily composed of carbon dioxide with thick clouds of sulfuric acid, making it one of the most inhospitable places in the solar system. If Earth moved closer to the Sun, we could expect a similar fate, with life unable to survive under the extreme heat and atmospheric pressure. On the other hand, if Earth were to move farther away from the Sun, it would receive less solar energy, leading to a cooling of the planet's surface. In this scenario, temperatures would drop, potentially causing global freezing and the loss of liquid water. Earth could become similar to Mars, a planet that sits farther from the Sun and is much colder. Mars's thin atmosphere cannot retain much heat, leading to average surface temperatures of around -80 degrees Fahrenheit, -60 degrees Celsius. Liquid water on Mars's surface is scarce, mostly found as ice at the polar caps, and any liquid water that does exist quickly evaporates or freezes due to the low atmospheric pressure and cold temperatures. If Earth moved farther from the Sun, it too would experience a deep freeze, with ice spreading across the planet and any remaining water becoming locked away as ice. The loss of liquid water would have a devastating impact on life on Earth, as nearly all known life forms depend on water to survive. Water is not only a crucial solvent in biological processes, but also plays a role in temperature regulation within organisms. Without liquid water, biochemical reactions necessary for life would slow down or stop entirely, and the diversity of life would be greatly diminished. The oceans, which regulate temperature and store heat, would freeze over, altering weather patterns and leading to extreme seasonal changes. The cooling of the planet would also slow down atmospheric and oceanic circulation, which would disrupt the climate further, creating a harsh and inhospitable environment. Even small changes in Earth's distance from the Sun would have effects on seasonal patterns. For instance, if Earth's orbit were more elliptical, with greater variation in its distance from the Sun, we would experience more extreme seasonal changes. Summers would be much hotter, and winters would be much colder, potentially making it difficult for ecosystems and species to adapt. Currently, Earth's orbit is nearly circular, which minimizes seasonal temperature extremes, and provides a stable climate that fosters biodiversity and ecosystem resilience. This stability is essential for the many species on Earth that have adapted to specific temperature ranges and seasonal patterns. Earth's exact distance from the Sun is also finely balanced with other factors that keep the climate in check. For instance, Earth's tilt on its axis creates the seasons, distributing solar energy more evenly over the planet's surface throughout the year. The tilt, combined with Earth's nearly circular orbit, ensures that solar energy is distributed in a way that supports diverse climates, from the tropical rainforests to the polar tundra. Additionally, Earth's rotation affects weather patterns and temperature by creating the day-night cycle, which helps regulate temperatures by allowing the planet to cool each night. This rotation, along with Earth's tilt and distance from the Sun, creates a climate system that is highly conducive to life. The anthropic principle. The anthropic principle is a concept that addresses one of the most intriguing questions about the universe. Why does it seem so perfectly suited for life? Why are the physical laws, constants, and conditions in our universe precisely what they need to be to allow the existence of stars, planets, and ultimately life? The anthropic principle proposes that the reason the universe appears fine-tuned for life is because we, as conscious beings capable of observation, are here to notice it. In other words, we wouldn't be around to observe a universe that didn't support life, so the fact that we are here to ask these questions means the universe must already have certain characteristics that make life possible. This principle has two main forms: the weak anthropic principle and the strong anthropic principle. The weak anthropic principle suggests that the universe's physical constants and conditions appear finely tuned, because only in a universe with such conditions could observers like us exist. It's a statement of necessity. We're here because the universe is the way it is, and if it were any different, we simply wouldn't be around to observe it. The strong anthropic principle, however, goes a step further, suggesting that the universe's properties aren't just coincidentally compatible with life, but are actually designed in a way that makes life inevitable. This idea implies a purpose behind the universe's existence, a notion that moves beyond physics into more philosophical or even theological realms. One of the most compelling reasons for the anthropic principle is the sheer improbability of the universe's fine-tuned constants. Take the gravitational constant as an example. This constant determines the strength of gravity, and if it were even slightly different, stars and galaxies might not have formed. A stronger gravitational force could have caused the universe to collapse back on itself shortly after the Big Bang, while a weaker force could have led to a universe where matter was so dispersed that stars and planets never coalesced. Similarly, the cosmological constant, which drives the expansion of the universe, has to be finely balanced. If it were even a tiny bit larger, the universe would have expanded too quickly for stars and galaxies to form. These and other constants appear so finely tuned that it raises the question of whether their values are a product of chance, necessity, or something else entirely. The multiverse hypothesis is one explanation for why the universe appears fine-tuned without invoking purposeful design. According to this theory, there isn't just one universe, but a vast, perhaps infinite number of universes, each with different physical laws and constants. In a multiverse, the conditions in each universe would vary, and most of these universes would likely be inhospitable to life. They could have physical constants that prevent stars from forming, or extreme energies that make stable matter impossible. But by sheer probability, some of these universes would happen to have the right conditions for life. Our universe, in this view, is simply one of the rare universes where conditions aligned in a way that allowed life to emerge, not because of intentional design, but because of statistical chance. If there are countless universes with different laws of physics, then it's inevitable that some of them, including ours, would possess the conditions necessary for life. The multiverse theory provides an interesting framework for understanding the anthropic principle. But it also raises questions that science is not yet equipped to answer. For one, if other universes exist, they would be beyond our ability to observe, making it difficult to gather empirical evidence for their existence. This lack of observational access makes the multiverse hypothesis a controversial idea, as it moves into a realm that some argue is closer to philosophy than to traditional science. However, some cosmologists see it as a natural extension of certain theories in quantum mechanics and cosmology, which suggest that multiple outcomes could occur across different parallel universes. The scientific implications of the anthropic principle and the multiverse theory are profound. They suggest that the laws of physics, which we often think of as universal and absolute, might be more like a set of possibilities that vary across different universes. This challenges the idea that our universe's laws are the only way things could be, opening up the possibility that reality itself is far more diverse and complex than we can currently comprehend. If the multiverse exists, then our understanding of what constitutes natural laws may need to be revised, as these laws would no longer be seen as constants of reality, but as specific to our universe alone. Beyond science, the anthropic principle has significant philosophical implications. It raises questions about existence, purpose, and the nature of reality. If the universe is indeed fine-tuned for life, does this suggest an underlying purpose or intention? Some interpret the anthropic principle as evidence of a kind of cosmic design, suggesting that the universe is structured in a way that allows for life, perhaps even with the implicit goal of giving rise to conscious observers. This interpretation can be appealing from a philosophical or spiritual perspective, as it implies that the universe has meaning or purpose beyond mere chance. Others, however, see the anthropic principle as an affirmation of randomness and probability rather than design. In this view, the conditions that allow for life are simply the result of a cosmic lottery. There is no deeper meaning behind the universe's structure. We just happen to be in one of the few universes where life is possible. For those who hold this perspective, the anthropic principle serves as a reminder of the vastness and indifference of the cosmos, where life emerges not through purpose but through sheer chance and statistical probability. One of the most profound questions raised by the anthropic principle is whether life is a universal inevitability or a rare cosmic accident. If the constants of our universe are finely tuned specifically to allow life, then life might indeed be an inherent part of the universe's design. On the other hand, if our universe is just one of many in a multiverse, then the emergence of life could be an incredibly rare occurrence, a 1 in a billion scenario that happened only because of specific and unlikely conditions. This question touches on the very nature of existence and what it means to be alive in a universe that seems so vast, mysterious, and finely balanced. The Moon's role. The Moon has been Earth's steadfast companion for billions of years, and its presence has a profound impact on our planet's stability and climate. One of the Moon's most important roles is in stabilizing Earth's axial tilt, the angle at which our planet is tilted in relation to its orbit around the Sun. This tilt, currently about 23.5 degrees, is responsible for our seasons, but it isn't fixed. Earth's tilt can fluctuate over long periods. The gravitational pull of the Moon acts as a stabilizing force, keeping these fluctuations within a narrow range. Without the Moon, Earth's tilt could vary dramatically, leading to extreme shifts in climate that could make the planet much less hospitable for life as we know it. The stability of Earth's axial tilt is crucial because it ensures a relatively consistent seasonal pattern. Our 23.5-degree tilt means that different parts of the Earth receive varying amounts of sunlight throughout the year, creating our seasons. During summer in the Northern Hemisphere, the North Pole tilts toward the Sun, bringing more direct sunlight and warmth, while in winter it tilts away, resulting in less direct sunlight and cooler temperatures. If Earth's tilt were to shift wildly, these seasonal differences would become extreme. For example, a larger tilt could lead to unbearably hot summers and freezing winters, making it difficult for ecosystems to adapt. Similarly, if the tilt were to decrease to near zero, Earth could lose its seasons entirely, resulting in a more monotonous climate that would drastically alter ecosystems and biodiversity. The Moon's gravitational influence prevents such chaotic shifts by exerting a stabilizing pull on Earth. This gravitational connection creates a kind of anchor that helps keep Earth's tilt steady. Over millions of years, the Moon's presence has kept Earth's axial tilt within a relatively narrow range of about 22 to 24.5 degrees. Scientists believe that without the Moon's stabilizing effect, Earth's tilt could vary by as much as 85 degrees, leading to severe climatic changes that would disrupt the planet's environmental balance. For life on Earth, this stability has been essential. A stable axial tilt allows for predictable seasonal changes, which in turn support the intricate cycles of life, from plant growth to animal migrations and reproduction. Each of these cycles has evolved in harmony with Earth's seasonal rhythms, creating a balanced and interconnected web of life. Beyond its role in stabilizing Earth's tilt, the Moon's gravitational pull also has a significant effect on our oceans. The Moon's gravity creates the tides, causing the water in the oceans to bulge outward on the side of Earth facing the Moon. As Earth rotates, this bulge moves across the surface, creating the familiar rise and fall of the tides. The tides have a profound impact on marine life, coastal ecosystems, and even the global climate. Tidal movement stirs the oceans, helping to distribute heat and nutrients. This circulation is essential for marine biodiversity, as it supports nutrient flow from the deep ocean to coastal regions, nourishing a variety of marine organisms and sustaining complex food chains. Tides are particularly important for coastal ecosystems, where the regular rise and fall of water levels create unique habitats that are home to an incredible diversity of life. Many coastal species, from fish and crabs to seabirds, have adapted their behaviors and life cycles to the rhythm of the tides. Tidal zones offer a range of environmental conditions, from areas that are submerged at high tide to areas that are exposed at low tide. This creates a dynamic environment that supports diverse communities of plants and animals, each adapted to specific tidal conditions. Without the Moon's gravitational pull, these ecosystems would be far less dynamic, potentially leading to a loss of biodiversity and disrupting the delicate balance of coastal life. The tidal forces created by the Moon also play a key role in ocean circulation, which has far-reaching effects on Earth's climate. The movement of ocean water driven by the tides contributes to global ocean currents, which distribute heat from the equator to the poles. This distribution of heat helps regulate the planet's climate, preventing the equator from becoming too hot and the poles from becoming too cold. Ocean currents like the Gulf Stream carry warm water from the tropics toward higher latitudes, moderating the climate in regions such as Western Europe. Without the Moon's influence on tides, these currents could be less stable or even absent, leading to more extreme temperatures and less predictable weather patterns. The Moon's gravitational pull on Earth has other subtle but important effects on our planet's rotation and the length of our days. The friction created by the tides gradually slows down Earth's rotation over time, which leads to an increase in the length of our days. Early in Earth's history, a day might have lasted only about 10 hours. But as the Moon's gravitational pull has slowed Earth's rotation, our days have lengthened to the 24-hour period we are familiar with today. This gradual slowing continues, adding a few milliseconds to the length of a day each century. While this may seem insignificant, it has been part of Earth's evolution, allowing for the development of a stable circadian rhythm that many species rely on for activities such as feeding, migration, and reproduction. The interaction between Earth and the Moon is also responsible for the phenomenon known as lunar recession. As Earth's rotation slows, some of its rotational energy is transferred to the Moon, causing the Moon to drift slowly away from Earth at a rate of about 3.8 centimeters per year. Over millions of years, this gradual recession has changed the distance between the Earth and the Moon, affecting the strength of tides and, by extension, Earth's climate. In the distant future, the continued recession of the Moon could lead to weaker tides, which would alter coastal ecosystems and impact the circulation patterns of the oceans. However, this process occurs over such long timescales that it will not affect life on Earth in the foreseeable future. Jupiter, the guardian of the solar system. Jupiter, the largest planet in our solar system, serves as a colossal cosmic shield for Earth. Its immense gravitational field acts as a protective barrier, capturing or deflecting many of the comets and asteroids that could otherwise pose a threat to Earth. Without Jupiter's gravitational influence, Earth would likely be far more exposed to dangerous impacts from space, which could have catastrophic consequences for life on our planet. Jupiter's presence in the solar system is a key factor in maintaining a relatively stable and safe environment for life on Earth. Jupiter's mass is about 318 times that of Earth, and its gravitational field is correspondingly powerful. Located in the outer solar system, just beyond the asteroid belt, Jupiter acts as a kind of gravitational gatekeeper. Its strong gravitational pull has a profound effect on the orbits of asteroids and comets, especially those that travel through the asteroid belt or originate from the more distant Kuiper belt and Oort cloud. When these objects enter the inner solar system, where they could cross paths with Earth, Jupiter's gravity can significantly alter their trajectories, often pulling them away from Earth or redirecting them entirely. One way that Jupiter protects Earth is by capturing potentially dangerous objects. When a comet or asteroid comes close to Jupiter, the planet's powerful gravity can pull it into a stable orbit around Jupiter, effectively trapping it and preventing it from reaching the inner solar system. In some cases, these objects may become Jovian moons, orbiting around Jupiter rather than continuing on a path toward Earth. This capture process prevents a number of objects from ever coming close to our planet. In addition to capturing objects, Jupiter can also deflect them. If an asteroid or comet comes near Jupiter at the right angle and speed, the planet's gravitational pull can act like a slingshot, redirecting the object's trajectory away from the inner solar system. This deflection effect is particularly important for objects that are on paths that could bring them close to Earth. By altering their course, Jupiter helps to shield Earth from potential impacts. This gravitational deflection is not just theoretical, it's been observed in action. In 1994, the comet Shoemaker-Levy 9 was pulled into Jupiter's gravity, eventually colliding with the planet in a series of spectacular impacts. Each fragment of the comet hit Jupiter's atmosphere with explosive force, releasing as much energy as millions of atomic bombs. If a similar-sized comet had struck Earth, the consequences could have been catastrophic. Instead, Jupiter's gravity redirected Shoemaker-Levy 9 away from Earth, demonstrating the protective role Jupiter plays. Another way Jupiter protects Earth is by clearing out debris from the asteroid belt and the outer solar system. Over billions of years, Jupiter's gravity has shaped the orbits of countless asteroids and comets, either capturing them, flinging them out of the solar system, or settling them into more stable orbits that don't threaten Earth. This long-term gravitational influence has reduced the number of objects that could potentially cross paths with our planet. The asteroid belt, located between Mars and Jupiter, contains millions of rocky objects, but the presence of Jupiter has limited the number of objects that stray into the inner solar system, where Earth orbits. Without Jupiter, Earth would face a much higher risk of impact events. While impacts from small meteors are relatively common, with many burning up in Earth's atmosphere before they can cause any damage, larger impacts are rare, but far more dangerous. A significant impact from an asteroid or comet could have catastrophic consequences, releasing massive amounts of energy and potentially triggering widespread environmental changes. Scientists believe that the extinction of the dinosaurs around 66 million years ago was caused by a large asteroid or comet impact, which led to drastic changes in Earth's climate. If Jupiter were not present to deflect or capture some of these objects, Earth might experience far more frequent impact events of similar scale, making life on our planet far less stable. Jupiter's protective role becomes even more significant when we consider the origin and movement of long-period comets. Unlike short-period comets, which originate from the Kuiper belt and have relatively short orbital periods, long-period comets come from the distant Oort cloud, a vast shell of icy objects that surrounds the solar system. These comets have orbits that can take thousands or even millions of years to complete, and when they do enter the inner solar system, they often travel at very high speeds. Because of their speed and size, impacts from long-period comets would be extremely destructive. Fortunately, Jupiter's gravitational influence extends far enough to affect some of these comets, pulling them away from potentially Earth-crossing paths, or even ejecting them from the solar system entirely. Jupiter's shielding effect is particularly important in the context of planetary habitability. Life on Earth has been able to evolve and thrive partly because our planet has experienced relatively few catastrophic impact events. This stability has allowed complex life forms to develop over millions of years without being frequently disrupted by massive impacts. In comparison, if Earth were located in a solar system without a large gas giant like Jupiter, it might be bombarded by comets and asteroids on a much more regular basis. This could make it difficult for life to gain a foothold, as repeated impacts could cause mass extinctions or severely alter the climate each time. The concept of Jupiter as a cosmic shield is supported by simulations and studies of planetary systems. Astronomers have found that gas giants like Jupiter play a similar protective role in other planetary systems, capturing or deflecting debris and helping to shield inner, potentially habitable planets. Observations of exoplanetary systems indicate that gas giants are common, and their presence could be an important factor in determining the habitability of planets in those systems. In this way, Jupiter's role as a cosmic shield may not be unique to our solar system, but could be a common feature in planetary systems with gas giants. The absence of Jupiter would also have consequences beyond the increased risk of impacts. The gravitational influence of Jupiter is so significant that it affects the orbits of other planets in the solar system, including Earth. Without Jupiter, the overall gravitational balance in the solar system would change, potentially leading to more chaotic orbits for the inner planets. The perfect tilt. Earth's 23.5-degree axial tilt is essential for life as we know it, driving the planet's seasonal changes and helping regulate climates across the globe. This tilt is the angle between Earth's rotational axis, imagined as a line passing through the North and South poles, and its orbit around the Sun. Rather than being perfectly perpendicular, Earth's axis leans at an angle of 23.5 degrees relative to its orbital plane. This seemingly small deviation has profound effects on Earth's climate, weather patterns, and the diversity of habitats and ecosystems. If Earth's tilt were significantly different, the planet's climate would be drastically altered, potentially reducing the conditions that make it hospitable for such a vast range of life. The primary effect of Earth's axial tilt is the creation of seasons, the predictable, regular divisions of the year that bring shifts in temperature, daylight, and precipitation patterns. These seasonal changes occur because Earth's tilt causes different parts of the planet to receive varying amounts of sunlight throughout its orbit around the Sun. During the summer solstice in the Northern Hemisphere, Earth's North Pole is tilted toward the Sun, which means the Northern Hemisphere receives more direct sunlight, resulting in warmer temperatures. Conversely, during the winter solstice, the North Pole is tilted away from the Sun, causing less direct sunlight to reach the Northern Hemisphere, and thus cooler temperatures. The opposite happens in the Southern Hemisphere, where summer occurs during the Northern Hemisphere's winter months, and vice versa. This annual cycle is a crucial driver of the diverse climates and habitats found on Earth. By distributing sunlight unevenly over the course of the year, Earth's tilt allows for a dynamic and varied climate that supports everything from tropical rainforests to temperate forests, deserts, and tundra. Each of these ecosystems has evolved in response to seasonal changes, creating a planet that supports an extraordinary range of life. Seasonal cycles dictate the rhythms of countless natural processes, from the migration of animals and the blooming of flowers to the growth of crops and the flow of rivers. The changing of the seasons drives ecosystems to adapt and evolve, promoting a biodiversity that would be difficult to sustain without these regular shifts in climate. Earth's tilt also plays a fundamental role in supporting agriculture, which is a cornerstone of human civilization. The predictable alternation between warm and cool seasons allows for the cultivation of a wide variety of crops suited to different climate conditions. Farmers can plant, grow, and harvest crops in harmony with seasonal cycles, producing reliable food supplies year after year. Seasonal changes bring the rains necessary for crop growth, and the period of warmer temperatures promotes photosynthesis, which is essential for plants to convert sunlight into the energy needed for growth. If Earth's tilt were absent or significantly altered, agriculture would be profoundly affected, potentially making it difficult to grow a wide variety of crops and disrupting the food supply that supports human societies. The 23.5 degrees tilt is not fixed, however. It can vary over long periods due to gravitational interactions with other celestial bodies, particularly the Moon and Jupiter. This phenomenon is known as axial precession. However, these variations are minor over human timescales, and Earth's tilt has remained within a relatively narrow range, which has helped maintain stable and predictable seasonal patterns. If this tilt were to shift dramatically, the effects on Earth's climate and ecosystems would be significant. A more extreme tilt, for example, closer to 45 degrees, would create harsh, prolonged seasons that could make life much more challenging. During summer, regions tilted toward the sun would experience intense, prolonged heat, as the sun would remain high in the sky for most of the day, creating scorching conditions that could lead to droughts and severe environmental stress. Winters, in contrast, would be equally extreme, with long periods of darkness and bitterly cold temperatures. These prolonged seasonal extremes would place enormous pressure on ecosystems, as plants and animals would have to endure extended periods of intense heat or cold. Some species might adapt, but many would struggle to survive under such extreme conditions. Biodiversity could suffer, as fewer organisms could withstand the drastic shifts in temperature and the long intervals between favorable conditions. Regions near the equator, which are typically less affected by seasonal changes, would also experience significant shifts in climate under an extreme tilt. Currently, the equator receives relatively consistent sunlight throughout the year, which supports lush tropical rainforests and rich biodiversity. However, with a more extreme tilt, even equatorial regions would experience substantial seasonal variation, disrupting the stable environment that many tropical species depend on. The delicate ecosystems of rainforests and coral reefs, already vulnerable to even slight changes in temperature, might struggle to adapt to these new conditions, leading to the loss of unique species and habitats. On the other hand, if Earth's tilt were closer to 0 degrees, seasonal variation would be minimal or even non-existent, creating a world with a more uniform climate throughout the year. While this might seem like it would promote stability, it would actually have serious implications for ecosystems and biodiversity. Without distinct seasons, much of the rhythm that drives life on Earth would disappear. Animals that migrate in response to seasonal changes, such as birds and marine species, would lose their cues to move between habitats. This could disrupt ecosystems and lead to declines in populations that depend on migration to find food, breed, or avoid harsh conditions. A reduced tilt would also impact the growth cycles of plants, which rely on seasonal changes in temperature and sunlight to regulate their reproductive processes. Trees in temperate regions, for example, shed their leaves in the fall to conserve energy during the winter months. Without seasonal cues, these cycles might become erratic or disappear altogether, leading to less diversity in plant life. Agriculture, too, would suffer under these conditions. Many crops are adapted to specific seasons and require certain environmental cues to trigger growth, flowering, or fruiting. Without seasons, crop yields could become less predictable and food supplies might be affected. In a world with little to no tilt, polar regions would likely be colder, as they would receive even less sunlight than they do now. However, equatorial regions would receive constant sunlight, leading to a more uniform but monotonous global climate. This would result in fewer unique climate zones and less environmental diversity. In effect, Earth's ecosystems would lose the dynamic variation that has allowed so many different forms of life to thrive. Biodiversity, which thrives on change and adaptation, would likely be reduced as species lost the environmental pressures that drive evolution and diversification. The consequences of tilt variations are evident when we look at other planets in our solar system with different axial tilts. For instance, Uranus has a tilt of about 98 degrees, which means it essentially rolls along its orbit with one pole facing the Sun for half of its journey around the Sun, and the other pole facing away for the other half. This extreme tilt creates incredibly harsh seasonal contrasts, with each pole experiencing about 42 years of continuous sunlight, followed by 42 years of darkness. Such conditions make it unlikely for complex life to evolve or survive. Mars, with a tilt similar to Earth's, but with greater variation over time, also experiences seasonal changes, though they are more extreme due to its thinner atmosphere and greater distance from the Sun. The stability of Earth's 23.5 degrees tilt, which is maintained in part by the gravitational influence of the Moon, has allowed for a climate that is both predictable and varied. This balance of seasonal change without excessive extremes has been fundamental to the evolution of life on Earth, supporting diverse habitats and promoting rich biodiversity. Our planet's ecosystems, agriculture, and even human societies have all developed in harmony with these seasonal cycles, creating a world where countless species can thrive. Earth's atmosphere. This layer of gases surrounds Earth, providing a protective barrier that regulates temperature, blocks harmful radiation, and allows for the complex chemical reactions that sustain life. Composed primarily of nitrogen, about 78%, and oxygen, about 21%, with trace amounts of argon, carbon dioxide, and other gases. The atmosphere has a carefully balanced composition that creates the right conditions for life to flourish. Additionally, the atmosphere is divided into distinct layers, each with unique properties that contribute to Earth's overall climate and protection. The troposphere is the lowest layer of the atmosphere, extending from Earth's surface to about 8 to 15 kilometers, 5 to 9 miles, up. This layer contains roughly 75% of the atmosphere's total mass, including most of the water vapor, which is crucial for weather and climate. The troposphere is where all of Earth's weather occurs. Clouds, rain, storms, and wind patterns are confined to this layer. It's also where greenhouse gases, such as carbon dioxide and methane, play a key role in trapping heat. This process, known as the greenhouse effect, allows the troposphere to maintain relatively stable temperatures that support life. Without the greenhouse effect, Earth's surface temperature would be significantly lower, likely dropping below freezing on average, which would make it difficult for life as we know it to survive. However, if the concentration of greenhouse gases increases too much, as we see with modern climate change, the troposphere can trap excessive heat, leading to global warming and climate instability. Above the troposphere lies the stratosphere, which extends from about 15 to 50 kilometers, 9 to 31 miles, above Earth's surface. This layer is most famous for its ozone layer, a region rich in ozone molecules that absorbs the majority of the sun's harmful ultraviolet UV radiation. UV radiation is highly energetic and can damage the DNA of living organisms, increasing the risk of mutations and health issues such as skin cancer. By absorbing UV radiation, the ozone layer acts as a protective shield, significantly reducing the amount of harmful radiation that reaches the surface. Without the ozone layer, life on Earth would be exposed to dangerously high levels of UV radiation, making the planet a much more hostile environment for most forms of life. Human activities, particularly the use of chlorofluorocarbons, CFCs, in the 20th century, once posed a major threat to the ozone layer, but international agreements like the Montreal Protocol have helped reduce ozone-depleting chemicals and promote the recovery of the ozone layer. The mesosphere lies above the stratosphere, extending from about 50 to 85 kilometers, 31 to 53 miles, above Earth's surface. In this layer, temperatures decrease with altitude, making it one of the coldest regions in the atmosphere. The mesosphere is also where meteors burn up upon entering Earth's atmosphere. As meteoroids enter the mesosphere, they encounter increasing air density, which creates friction and causes them to heat up and disintegrate before reaching the surface. This natural defense mechanism protects Earth from a constant barrage of meteoroids and other small celestial objects that could otherwise pose a threat to life on the surface. Next is the thermosphere, which extends from about 85 kilometers to 600 kilometers, 53 to 373 miles above Earth. This layer has very low air density and is characterized by extremely high temperatures, often reaching thousands of degrees due to the absorption of intense solar radiation. The thermosphere is also home to the ionosphere, a region where solar radiation ionizes gas molecules, creating ions that reflect and transmit radio waves. This ionized layer is crucial for long-distance radio communication, as it allows radio signals to bounce back to Earth rather than escaping into space. The thermosphere is also where the auroras occur, stunning light displays created by interactions between solar wind particles and the Earth's magnetic field. The thermosphere's role in absorbing solar energy also helps protect lower atmospheric layers from intense radiation. Beyond the thermosphere is the exosphere, the outermost layer of Earth's atmosphere. This layer extends from around 600 kilometers, 373 miles, above Earth's surface and gradually fades into the vacuum of space. The exosphere is composed mainly of hydrogen and helium, and it is so thin that individual gas particles can travel hundreds of kilometers without colliding. While the exosphere plays a minimal role in Earth's climate or weather, it serves as the boundary between Earth's atmosphere and outer space, with only the faintest trace of air. The delicate balance of Earth's atmospheric layers and composition is crucial for maintaining a stable climate and protecting life. But what would happen if the atmosphere was significantly thicker or thinner? Each scenario would lead to dramatic changes that could render Earth uninhabitable. If Earth's atmosphere were thicker, it would likely trap much more heat, creating a situation similar to the runaway greenhouse effect observed on Venus. Venus, which has an atmosphere about 90 times thicker than Earth's, experiences surface temperatures exceeding 450 degrees Celsius, 842 degrees Fahrenheit, due to the intense greenhouse effect. The thick carbon dioxide-rich atmosphere of Venus traps so much heat that it creates a constant searing climate with little to no temperature variation between day and night or across seasons. If Earth had a similarly thick atmosphere, it would trap excessive amounts of solar radiation, leading to extreme heat on the surface. Water bodies would evaporate, and the increased water vapor, a powerful greenhouse gas, would further trap heat, exacerbating the warming. Eventually, Earth's oceans could disappear, and the planet would become a hot, barren world unable to support life as we know it. In addition to trapping heat, a thicker atmosphere would also increase surface pressure. Higher atmospheric pressure would have a range of effects on both the environment and living organisms. For instance, with increased pressure, it would be more difficult for organisms to breathe and for water to evaporate, altering natural processes and potentially challenging the survival of many species. Plants, which rely on water vapor exchange to carry out photosynthesis, might struggle under these altered conditions, disrupting the food chain and destabilizing ecosystems. On the other hand, if Earth's atmosphere was significantly thinner, it would provide far less insulation, leading to lower average temperatures on the surface. The thinner atmosphere would retain less heat from the sun, making Earth's climate colder, especially at night. Earth might start to resemble Mars, which has an atmosphere less than 1% as dense as Earth's and lacks a significant greenhouse effect. As a result, Mars experiences extreme temperature fluctuations with warm days and freezing nights. A thinner atmosphere on Earth would lead to similar fluctuations, making it challenging for complex life to survive. Plants and animals would struggle to adapt to the rapid temperature changes, and the stability required for diverse ecosystems would be compromised. A thinner atmosphere would also offer much less protection from harmful solar and cosmic radiation. Currently, Earth's atmosphere and magnetic field together create a shield that blocks or deflects most of this high-energy radiation, which can damage DNA and increase cancer risk. With a thinner atmosphere, more radiation would reach Earth's surface, posing a direct threat to life. Additionally, the ozone layer, located in the stratosphere, would likely be reduced or non-existent in a thinner atmosphere. Without the ozone layer's protection, Earth would be exposed to intense UV radiation, which can harm organisms, damage crops, and disrupt ecosystems. Another consequence of a thinner atmosphere would be a reduction in meteor shielding. Earth's atmosphere acts as a protective barrier, causing most meteors to burn up in the mesosphere before they can reach the surface. Without this layer of protection, Earth would experience far more frequent meteor impacts, ranging from small meteors to potentially larger ones capable of causing significant damage. Over time, the increased frequency of impacts could alter Earth's surface and create an unstable environment, increasing the risk of life-threatening events. The composition of the atmosphere is equally important as its thickness. The current balance of gases in Earth's atmosphere is ideal for sustaining life. Oxygen is essential for most animal life, while nitrogen plays a key role in stabilizing the atmosphere. If these proportions were to shift dramatically, the effects on life would be profound. For instance, an increase in oxygen levels could lead to more intense wildfires, as oxygen supports combustion. Conversely, a decrease in oxygen could make it harder for organisms to breathe, impacting metabolic processes and threatening many species. Magnetic field, Earth's invisible shield. Generated by the motion of molten iron within Earth's outer core, this magnetic field extends far into space, creating a protective barrier known as the magnetosphere. The magnetosphere acts as a shield, deflecting charged particles from the solar wind, a continuous stream of high-energy particles, primarily protons and electrons, emitted by the Sun. This magnetic shield prevents these particles from reaching Earth's atmosphere directly, where they could have devastating consequences for both the atmosphere and life on the surface. The magnetic field is therefore essential, not only for protecting life from harmful radiation, but also for maintaining the stability of Earth's atmosphere, which in turn helps to sustain the planet's climate and biosphere. The solar wind is a powerful force in the solar system, constantly bombarding planets and other celestial bodies with streams of high-energy particles. These particles are ejected from the Sun's outer layers at high speeds, carrying with them magnetic fields that interact with any object in their path. For planets without a strong magnetic field, the solar wind can strip away the outer layers of their atmospheres, leading to a gradual but devastating loss of gases essential for supporting life. Mars, for example, is thought to have once had a thick atmosphere and liquid water on its surface, but without a significant magnetic field, it has lost much of its atmosphere over billions of years, likely due to the erosive effects of solar wind. Earth's magnetic field, by contrast, has acted as a protective shield, deflecting these particles and preventing the atmosphere from being stripped away in a similar fashion. The magnetic field achieves this protection through a phenomenon known as magnetic deflection. When charged particles from the solar wind encounter Earth's magnetic field, they are redirected around the planet, following the magnetic field lines and being funneled toward the poles, where the field is weaker. This redirection keeps most of the particles away from the atmosphere, creating a protective bubble that shelters Earth from the direct impact of the solar wind. The interaction between solar particles and Earth's magnetic field also gives rise to the auroras, the beautiful light displays seen near the polar regions. When charged particles collide with atoms in the upper atmosphere, They produce bursts of light that create the auroras, also known as the northern and southern lights. These light displays are a visible reminder of Earth's magnetic shield at work. Earth's magnetic field not only protects against the solar wind, but also blocks cosmic radiation, high-energy particles that originate from outside the solar system. These cosmic rays are remnants of supernova explosions and other violent cosmic events. Without the magnetic field, cosmic rays would more readily penetrate Earth's atmosphere, exposing the surface and its inhabitants to dangerous levels of radiation. Over time, this increased exposure to radiation would have serious biological effects, as radiation can damage DNA and increase the risk of mutations, cancers, and other health issues. For early life forms especially, this protection would have been crucial, as high radiation levels could have interfered with the delicate processes of evolution. The importance of the magnetic field extends beyond radiation shielding. It plays a fundamental role in preserving Earth's atmosphere, a critical factor for maintaining a stable climate and allowing water to exist in liquid form. If Earth's atmosphere were to be significantly eroded by solar wind, the loss of gases, including water vapor, would eventually reduce the greenhouse effect, cooling the planet's surface and making it more difficult for life to thrive. This gradual cooling could even lead to a snowball Earth scenario, where temperatures drop so drastically that the planet is engulfed in ice, halting many of the natural processes essential for sustaining life. The magnetic field, by preventing atmospheric erosion, helps keep Earth's climate stable, creating the conditions necessary for a diverse range of ecosystems to develop and flourish. However, Earth's magnetic field is not constant. Over time, the strength of the field can vary, and it even undergoes occasional magnetic reversals, where the north and south magnetic poles switch places. This phenomenon occurs over thousands to millions of years, with the last reversal taking place about 780,000 years ago. During these periods, the magnetic field weakens, which would seem to expose Earth to increased radiation and atmospheric erosion. But even during these reversals, the field does not disappear entirely. Rather, it becomes more complex, with multiple poles appearing and interacting in ways that still offer some level of protection. Scientists continue to study these reversals to understand how life on Earth has persisted through them, but it is generally believed that the magnetic field, even in a weakened state, still provides sufficient shielding against harmful particles. If Earth's magnetic field were to weaken significantly or even disappear, the consequences could be dire. Without this protective shield, Earth's atmosphere would be vulnerable to the full impact of the solar wind, which could erode it over time. This atmospheric loss would first affect the upper layers, particularly lighter gases like hydrogen, which are essential for forming water molecules. As hydrogen escapes into space, the remaining gases could also be stripped away, reducing the atmosphere's ability to trap heat and maintain stable surface temperatures. Over millions of years, this process could transform Earth's climate, potentially making it as barren and hostile as Mars. A weaker or absent magnetic field would also mean increased exposure to solar and cosmic radiation. Higher levels of radiation would not only pose health risks for all life forms, but could also interfere with technological infrastructure. High-energy particles can damage electronic equipment, satellites, and communication networks, making it more challenging to maintain modern society. Solar storms, in particular, could have more severe impacts, as intense bursts of solar wind could disrupt power grids, GPS systems, and other critical technologies. For human space exploration, the lack of a magnetic shield would pose a substantial challenge, as astronauts would face higher levels of radiation without the natural protection provided by Earth's magnetosphere. The role of the magnetic field in protecting biodiversity is also profound. Earth's ecosystems have evolved in an environment where the magnetic field has kept radiation exposure at manageable levels. Increased radiation would have cascading effects on food chains and ecosystems, as some species are more vulnerable to radiation than others. For example, many microorganisms, which form the basis of numerous food webs, could suffer from increased mutation rates and disrupted reproduction due to radiation exposure. This, in turn, could impact larger organisms that depend on these microorganisms, potentially leading to a decline in biodiversity and altering the balance of ecosystems. The protection offered by Earth's magnetic field is particularly important in the context of atmospheric retention. As mentioned, the solar wind can strip away atmospheric particles, especially when a planet lacks a strong magnetic field. Mars is an example of this phenomenon. It likely had a thicker atmosphere and liquid water billions of years ago, but without a magnetic field, the solar wind gradually eroded its atmosphere, leaving it with only a thin layer of gas. Mars is now cold, dry, and unable to support liquid water on its surface due to the loss of atmospheric pressure. Earth's magnetic field has prevented a similar fate by shielding the atmosphere from this erosive process. Earth's magnetic field has also been critical in the development and evolution of life. Early life forms, which emerged billions of years ago, were likely more vulnerable to changes in radiation levels than many modern species. The magnetic field's ability to shield the surface from intense radiation may have provided the stable conditions needed for early organisms to thrive and evolve into more complex forms of life. This protection was especially important before the development of the ozone layer, which now offers additional UV protection. As life evolved, the magnetic field continued to offer stability, protecting ecosystems and allowing complex organisms to survive without constant exposure to harmful radiation. The carbon cycle. The carbon cycle is one of Earth's most vital processes, functioning as a natural thermostat that regulates atmospheric levels of carbon dioxide, CO2, and maintains stable global temperatures. This cycle involves the continuous movement of carbon through the atmosphere, oceans, soil, plants, and animals, driven by both biological and geological processes. By keeping CO2 levels balanced, the carbon cycle helps moderate Earth's climate, creating the conditions necessary for life to thrive. Any disruption to this balance, whether an excess of CO2, which contributes to warming, or a depletion of CO2, which leads to cooling, can have significant consequences for global temperatures, weather patterns, and ecosystems. At the core of the carbon cycle is the exchange of carbon between the atmosphere and living organisms. Plants, algae, and certain bacteria absorb CO2 from the atmosphere through photosynthesis, a process that converts carbon dioxide and sunlight into glucose, which serves as an energy source for growth. During photosynthesis, oxygen is released as a byproduct, enriching the atmosphere and supporting aerobic life. This carbon, now stored in plant tissue, enters the food chain as animals consume plants, moving the carbon through the ecosystem. Eventually, when plants and animals die, decomposers like bacteria and fungi break down organic material, releasing CO2 back into the atmosphere through respiration. In addition to biological processes, the carbon cycle includes geological processes that store carbon for extended periods. When plants and animals die, some of their organic material is buried and eventually transforms into fossil fuels like coal, oil, and natural gas over millions of years. This carbon remains locked in the Earth's crust until it is released through volcanic activity or human activities, such as burning fossil fuels. Another significant geological process is the weathering of rocks, which absorbs CO2 from the atmosphere and stores it in the form of carbonate minerals. These rocks eventually make their way back to the Earth's surface through tectonic activity, where they may release carbon again through volcanic eruptions. The oceans also play a critical role in the carbon cycle by acting as a massive carbon sink. CO2 from the atmosphere dissolves in the surface waters of the ocean, where it can be used by marine organisms like plankton in photosynthesis. Some of this carbon is stored in the bodies of marine organisms and upon their death sinks to the ocean floor, where it can be sequestered for long periods in sediments. Ocean circulation moves this carbon-rich water around the globe, helping distribute carbon and regulate atmospheric levels. The ability of oceans to absorb and store CO2 has been essential in mitigating climate change by removing a portion of excess CO2 from the atmosphere, though this capacity is not unlimited. The carbon cycle serves as Earth's natural thermostat by balancing the amount of CO2 in the atmosphere, which is crucial for regulating temperatures. CO2 is a greenhouse gas, meaning it traps heat in the atmosphere and helps maintain Earth's surface temperature at a level that supports life. Without greenhouse gases like CO2, Earth would be significantly colder, potentially too cold to sustain life as we know it. However, because CO2 also has the potential to cause warming, maintaining its levels within a narrow range is essential for climate stability. This balance is typically achieved through the interplay of carbon-absorbing and carbon-releasing processes. When the carbon cycle is in balance, the amount of CO2 removed from the atmosphere through photosynthesis, ocean absorption, and rock weathering roughly matches the amount released through respiration, volcanic activity, and other processes. This balance allows Earth's climate to remain relatively stable over long periods, with gradual fluctuations that ecosystems can adapt to. However, when this balance is disrupted, such as by an excess release of CO2, the climate can be significantly impacted, leading to changes that occur too quickly for ecosystems and species to adapt. One of the main causes of carbon cycle disruption today is human activity, particularly the burning of fossil fuels. Fossil fuels, which took millions of years to form, release vast amounts of CO2 when burned for energy, effectively short-circuiting the carbon cycle by introducing stored carbon directly into the atmosphere. This has led to a rapid increase in atmospheric CO2 levels, intensifying the greenhouse effect and contributing to global warming. Unlike natural sources of CO2, which are typically balanced by carbon sinks, human-generated CO2 overwhelms the natural processes that remove carbon from the atmosphere, leading to a net increase in greenhouse gases. The consequences of excess CO2 in the atmosphere are profound. The additional greenhouse gases trap more heat, leading to higher global temperatures, shifts in weather patterns, and more extreme weather events. Rising temperatures disrupt ecosystems by changing the habitats and conditions that species depend on. For instance, polar regions are warming faster than the global average, causing sea ice to melt and endangering species like polar bears that rely on ice for hunting and habitat. Ocean temperatures are also rising, which affects marine ecosystems and causes coral bleaching, a phenomenon where coral reefs lose the algae they depend on for energy, leading to widespread reef die-offs. Excess CO2 also leads to ocean acidification, as more CO2 dissolves into seawater, forming carbonic acid. This lowers the pH of the ocean, making it more acidic. Acidic waters threaten marine life, particularly species with calcium carbonate shells, such as coral, mollusks, and certain types of plankton. These organisms struggle to form and maintain their shells in acidic conditions, which has ripple effects throughout the marine food web. As foundational species in ocean ecosystems decline, the species that depend on them are also at risk, disrupting food chains and reducing biodiversity. Conversely, if CO2 levels were depleted to significantly lower levels, Earth would face a different set of challenges. Less atmospheric CO2 would mean a weaker greenhouse effect, causing global temperatures to drop. This could lead to a cooling trend severe enough to trigger ice ages, periods marked by extensive glaciation and colder temperatures worldwide. With less heat retained in the atmosphere, Earth's climate would become much harsher, especially in higher latitudes, where conditions would be too cold to support much of the existing life. Vegetation zones would shift as forests and grasslands shrink and tundra and ice spread further south, reducing habitats for countless species and destabilizing ecosystems. The balance of the carbon cycle is not only essential for climate stability, but also for the health of terrestrial ecosystems. Plants, for example, rely on CO2 for photosynthesis, so they are directly affected by changes in atmospheric CO2 levels. Increases in CO2 can stimulate plant growth, a phenomenon known as the CO2 fertilization effect. However, while elevated CO2 levels may benefit some plants, other factors such as soil nutrients and water availability often limit plant growth, preventing the carbon cycle from simply absorbing all excess CO2 through vegetation. Furthermore, rapid climate changes associated with excess CO2, such as droughts and heat waves, can harm plant communities more than they benefit from increased CO2. Disruptions to the carbon cycle also impact soil health and carbon storage. Plants absorb CO2 and store it in their biomass, and when they die, this carbon is transferred to the soil. Microorganisms in the soil decompose organic matter, releasing CO2 back into the atmosphere and continuing the carbon cycle. However, changes in climate, such as increased temperatures or shifting precipitation patterns, can affect the rate of decomposition and soil carbon storage, potentially releasing even more CO2 into the atmosphere and further intensifying warming. The Sun's stability. The Sun's stability is one of the most critical factors in the development and sustainability of life on Earth. As a main sequence star, the Sun has been emitting a stable and consistent output of energy for billions of years, creating the conditions necessary for life to emerge and evolve on our planet. The Sun's energy output provides Earth with light, heat, and a relatively constant climate, all of which are crucial for maintaining ecosystems and supporting diverse forms of life. If the Sun were less stable or significantly different in size, Earth's climate and habitability would be profoundly affected, potentially preventing life from evolving in the way we know it. The Sun is currently in the main sequence phase of its life cycle, a stage where it fuses hydrogen into helium in its core, releasing energy in the form of light and heat. This phase is marked by remarkable stability, as the balance between the gravitational forces pulling inward and the pressure created by nuclear fusion pushing outward creates a steady and controlled release of energy. The Sun has been in this stable phase for about 4.6 billion years and is expected to remain so for another 5 billion years. This extended period of stability allows planets like Earth to maintain a consistent climate over vast stretches of time, providing a stable environment in which complex life can evolve. The lifespan of a main sequence star like the Sun is largely determined by its mass. The Sun, classified as a G-type main sequence star, or G-dwarf, is considered a medium-sized star with an ideal balance of mass and energy output for sustaining life on surrounding planets. Larger, more massive stars tend to have much shorter lifespans because they burn through their nuclear fuel more quickly. For instance, massive stars that are several times the size of the Sun can exhaust their hydrogen supply in just a few million years compared to the Sun's multi-billion-year lifespan. This rapid consumption of fuel leads to a short-lived, highly energetic life cycle, leaving little time for planets orbiting such stars to cool, stabilize, and develop the necessary conditions for life. If the Sun were more massive, it would have burned much more brightly and intensely, producing far more heat and radiation. In this scenario, the young Earth would have been subjected to extreme conditions, making it difficult, if not impossible, for liquid water to persist on its surface. Any life that managed to emerge under these harsh conditions would have had a very limited window in which to evolve and adapt. A more massive Sun would also progress through its life cycle much faster, exhausting its hydrogen fuel and moving into the next phase of stellar evolution in just a few million years. This brief period would be insufficient for complex organisms to evolve, given that life on Earth took billions of years to transition from simple single-celled organisms to complex, multicellular life. On the other hand, if the Sun were less massive, it would produce less heat and light, making it more challenging for Earth to maintain temperatures conducive to liquid water and life. A less massive star would also have a weaker gravitational pull, which could affect the structure and stability of the solar system. Planets like Earth might orbit farther away or follow less stable paths, leading to erratic climates that would be less hospitable for life. Smaller stars also have a tendency to produce intense stellar flares and high-energy radiation, which can create harsh conditions for planets within their habitable zones. The Sun's consistency as a main sequence star provides Earth with a stable climate over long periods, which is crucial for maintaining the delicate balance required by ecosystems. Without this stability, the climate on Earth could experience wild fluctuations that would disrupt life cycles and food webs. Complex ecosystems depend on reliable seasonal changes and consistent weather patterns, both of which are made possible by the Sun's stable energy output. By providing a steady flow of energy, the Sun ensures that the temperatures on Earth remain within a range that supports diverse habitats, from tropical rainforests to polar ice caps. Additionally, the Sun's stability allows Earth's atmosphere to remain relatively stable. If the Sun's energy output fluctuated dramatically, Earth's atmosphere could be thrown into disarray. For example, a sudden increase in solar energy would cause the atmosphere to heat up rapidly, leading to changes in weather patterns, increased evaporation of water, and potentially devastating consequences for ecosystems. Conversely, a decrease in solar output would lead to cooling, which could cause widespread glaciation and a reduction in habitable areas. The Sun's consistent energy output is therefore essential for maintaining the balance of Earth's atmosphere, climate, and ecosystems. An unstable Sun would also pose significant risks to human infrastructure and technology. Many modern technologies, including satellite communications, GPS, and power grids, are sensitive to solar activity. Sudden solar flares or bursts of radiation can disrupt these systems, causing power outages and communication failures. A more variable Sun, prone to frequent and intense solar flares, would make it challenging to maintain reliable technology on Earth, affecting everything from daily communications to global navigation systems. In addition to stability, the main sequence phase of the Sun provides enough time for life to evolve and diversify. Life on Earth has taken billions of years to progress from simple microorganisms to complex multicellular organisms, and this gradual evolution has relied on the consistent conditions provided by the Sun. If the Sun's lifespan were shorter, there would be less time for evolutionary processes to unfold, making it unlikely that complex life could develop. The slow, predictable progression of the Sun as a main sequence star has given Earth's biosphere the time it needs to adapt, diversify, and respond to environmental changes. As a main sequence star, the Sun also maintains a habitable zone, the region around a star where conditions are suitable for liquid water to exist. Earth's position within this habitable zone allows it to receive just the right amount of energy to keep its surface temperatures within a range that supports life. If the Sun's energy output varied too much, Earth could either move out of this habitable zone or experience drastic temperature changes, making it difficult for ecosystems to remain stable. The stability of the Sun as a main sequence star ensures that Earth remains in this habitable zone for billions of years, providing a stable environment in which life can thrive. The Sun's stability has not only allowed for the evolution of life on Earth, but has also influenced the development of Earth's climate system. The Sun's consistent output of energy drives weather patterns, ocean currents, and the water cycle, all of which are essential for regulating temperatures and distributing heat around the planet. The interaction between sunlight and Earth's atmosphere generates wind patterns, which influence weather and climate across the globe. Ocean currents, driven by the Sun's heat, transport warm water from the equator to the poles, helping to moderate temperatures and maintain a balanced climate. If the Sun were more massive and less stable, its energy output would likely fluctuate, causing unpredictable shifts in Earth's climate. Such variability would make it difficult for life to adapt to the changing conditions, as plants and animals rely on predictable seasonal patterns for reproduction, migration, and survival. By providing a steady source of energy, the Sun has allowed Earth's climate system to evolve in a way that supports life across diverse habitats and ecosystems. In contrast, stars that are less stable often produce solar flares and bursts of high-energy radiation, which can be harmful to life on nearby planets. Some stars, known as flare stars, are prone to sudden outbursts that release large amounts of radiation. If the Sun was similar to a flare star, Earth would be subjected to frequent radiation storms that could damage the atmosphere and increase the risk of mutations and radiation-related health issues in living organisms. The Sun's stable output minimizes these risks, creating a more predictable and less hazardous environment for life. The Sun's stability as a main sequence star will not last forever, but its predictable progression allows scientists to anticipate changes. In approximately 5 billion years, the Sun will exhaust its hydrogen fuel and enter the red giant phase, expanding and engulfing the inner planets, including possibly Earth. However, the gradual nature of this process provides a vast timescale for life on Earth to continue evolving and adapting. Until then, the Sun's stable main sequence phase offers the consistency needed to support complex life. Plate tectonics, the engine of life. Plate tectonics is one of the most fundamental processes on Earth, playing a crucial role in shaping the planet's surface, regulating the climate, and even supporting life itself. This geological process involves the movement of the Earth's lithosphere, large, rigid plates that float on the semi-fluid asthenosphere beneath. Driven by the heat and dynamic forces within Earth's mantle, tectonic activity causes these plates to move, interact, and reshape the surface over millions of years. These movements result in the formation of mountains, ocean basins, and volcanic activity, which in turn contribute to Earth's unique habitability. Without plate tectonics, Earth would likely be a stagnant, geologically inactive world, lacking the necessary mechanisms to sustain life as we know it. One of the most significant roles of plate tectonics is in geological recycling, which keeps essential nutrients, minerals, and carbon circulating through the Earth's crust, atmosphere, and oceans. This recycling process is driven by two main types of plate boundaries: divergent boundaries, where plates move apart, and convergent boundaries, where plates move toward each other. At divergent boundaries, such as the Mid-Atlantic Ridge, magma rises from the mantle to fill the gap between separating plates, creating new oceanic crust. Over time, this crust moves away from the ridge and eventually sinks back into the mantle at subduction zones, convergent boundaries, where one plate is forced beneath another. Through these processes, Earth's surface is continuously renewed, preventing nutrient depletion and enabling the constant availability of elements necessary for life. Volcanic activity, a direct result of plate tectonics, plays a crucial role in releasing minerals and gases into the atmosphere, oceans, and soils. When volcanoes erupt, they release gases like carbon dioxide, CO2, and sulfur dioxide, SO2, along with various minerals essential for life. CO2 released by volcanic activity contributes to the carbon cycle, a natural process that regulates atmospheric CO2 levels and maintains a stable climate. Volcanic rocks, once weathered and broken down, contribute minerals like phosphorus, potassium, and magnesium to the soil, which are essential nutrients for plants. This nutrient cycling ensures that ecosystems remain productive and fertile over geological timescales, supporting the growth of vegetation and, in turn, the animals that rely on plant life. Plate tectonics is also closely linked to the carbon cycle, one of Earth's primary mechanisms for regulating climate. The carbon cycle operates through a balance of carbon sources and sinks, with plate tectonics playing a role in both. When volcanic eruptions release CO2 into the atmosphere, it contributes to the greenhouse effect, which traps heat and warms the planet. However, CO2 is also removed from the atmosphere through processes like chemical weathering, where carbonic acid in rainwater reacts with rocks to form bicarbonates. These bicarbonates are carried to the ocean, where they eventually become part of the sediments on the ocean floor. Over time, these sediments are subducted into the mantle at convergent plate boundaries, sequestering carbon deep within the Earth. This process is a long-term carbon sink, removing CO2 from the atmosphere and stabilizing the planet's climate. Without plate tectonics, Earth would lack this natural thermostat. The carbon cycle would be disrupted, and CO2 levels in the atmosphere would fluctuate wildly, potentially leading to either extreme greenhouse conditions or a frozen, inhospitable planet. The balance between volcanic CO2 emissions and carbon sequestration through tectonic subduction helps maintain Earth's temperature within a range that supports liquid water and life. This balance is crucial for preventing runaway greenhouse effects, such as those seen on Venus, or severe cooling that could lead to a snowball Earth scenario where ice covers much of the planet's surface. Plate tectonics also influences ocean circulation, which plays a vital role in regulating global temperatures and climate patterns. Mid-ocean ridges, formed by divergent tectonic plates, create new oceanic crust that gradually moves across the ocean floor. This movement drives ocean currents, which help distribute heat from the equator to the poles, creating a relatively stable climate across the planet. Additionally, the movement of tectonic plates contributes to the formation of ocean basins and the cyclical rise and fall of sea levels, affecting marine ecosystems and nutrient distribution. Ocean circulation patterns are essential for the health of marine ecosystems, which rely on the upwelling of nutrient-rich waters to support plankton growth, the foundation of the marine food web. One of the most profound effects of tectonic activity is on biological evolution. By reshaping Earth's surface, creating mountains, and forming islands, plate tectonics has created diverse habitats and promoted the isolation of species. Geographic isolation, such as that seen on islands or in mountain valleys, encourages species to adapt to their specific environments, leading to speciation, the process by which new species evolve. This process has given rise to Earth's incredible biodiversity, as species evolve to fill different ecological niches across the varied landscapes shaped by tectonic forces. The unique biodiversity of islands like the Galapagos and Madagascar, where species have evolved in isolation, is a direct result of tectonic activity and the dynamic reshaping of Earth's surface. In addition to fostering biodiversity, plate tectonics provides a geological cycle of renewal that helps sustain ecosystems over long periods. As tectonic plates collide, mountains form, and as these mountains erode over millions of years, they release nutrients back into the soil and rivers, replenishing areas that would otherwise become depleted. This cycle of mountain building and erosion ensures a continuous supply of essential minerals to ecosystems, allowing plants to grow and support complex food chains. Without this process, soils would eventually become nutrient poor, leading to declines in plant productivity and consequently a loss of biodiversity. If Earth were a stagnant planet without tectonic activity, it would eventually become geologically inactive, with severe consequences for its habitability. Without tectonic movements, there would be no volcanic activity to release new CO2 into the atmosphere, leading to a gradual depletion of atmospheric carbon over millions of years. The lack of volcanic eruptions would also mean a lack of mineral renewal in the soil, leading to nutrient-poor soils that would struggle to support plant life. Without fresh mineral deposits, many ecosystems would face nutrient shortages, resulting in declining plant productivity and, ultimately, less food for herbivores and carnivores alike. A stagnant Earth would also lack the tectonic mechanisms necessary to sequester carbon. The subduction of oceanic plates, which carries carbon-rich sediments into the mantle, would cease, leading to a buildup of atmospheric CO2. This could destabilize Earth's climate, causing either excessive cooling or warming, depending on how other parts of the carbon cycle are affected. The delicate balance that maintains Earth's temperature within a life-supporting range would be lost, making the planet vulnerable to climate extremes. Without plate tectonics, Earth's atmosphere and oceans would lack long-term regulation. Over time, carbon dioxide levels in the atmosphere would likely decline, potentially cooling the planet and making it less hospitable to life. Additionally, without tectonic activity, the oceans would lose their dynamic circulation patterns, becoming more stagnant. This stagnation would prevent the natural upwelling of nutrients, leading to a less productive ocean environment and a decline in marine biodiversity. Earth's ecosystems, both terrestrial and marine, would suffer from reduced nutrient availability and a less stable climate, making it harder for life to thrive. Furthermore, the absence of tectonic activity would impact geological hazards that, despite their destructive power, play a role in shaping Earth's surface and influencing evolution. Volcanic eruptions, earthquakes, and mountain-building events are part of Earth's natural processes. And while they can be destructive, they also create new habitats and force species to adapt to changing environments. These events drive natural selection, leading to the evolution of traits that help species survive in dynamic environments. A stagnant, inactive planet would lack these forces, resulting in a less diverse and adaptive biosphere over time. The universe's perfect solvent. Water is often called the universal solvent for a reason. Its unique properties make it indispensable to life on Earth. From stabilizing temperatures to supporting countless chemical reactions, water is the foundation upon which almost all biological processes depend. It's not just that water is abundant on our planet, but that its molecular structure gives it specific qualities unlike any other liquid. These properties have shaped Earth's climate, ecosystems, and the very processes that make life possible. Without water, or if a different solvent took its place, life as we know it would simply not exist. One of water's most remarkable features is its high specific heat capacity. Specific heat is the amount of energy needed to raise the temperature of a substance by a certain amount, and water's specific heat is higher than almost any other liquid. This means it takes a lot of energy to heat up or cool down water, which has a stabilizing effect on temperatures. For Earth, this is crucial. Large bodies of water, like oceans, absorb and release heat slowly, helping to moderate global temperatures. During the day, oceans absorb heat from the sun, keeping coastal areas cooler. At night, they release this stored heat, preventing temperatures from plummeting. This creates a more stable climate overall, and these thermal properties of water ensure that temperature fluctuations are limited, supporting a wide range of ecosystems and allowing organisms to survive within stable temperature ranges. The high specific heat capacity of water is also vital for organisms themselves. Living beings, especially animals, consist largely of water, which helps them maintain stable internal temperatures. This is particularly important for warm-blooded animals, whose survival depends on keeping their body temperature within a narrow range. When environmental temperatures rise or fall suddenly, the water within an organism acts as a buffer, resisting rapid changes in body temperature. This thermal stability is fundamental for complex life, allowing enzymes and biochemical processes to function consistently without being disrupted by external temperature shifts. Another critical property of water is its ability to dissolve a vast range of substances, earning it the title of the universal solvent. This quality is essential for life because it allows water to carry nutrients, minerals, and other essential compounds throughout the bodies of organisms. Water dissolves ions and molecules, making them available for cells to use in metabolic reactions. In plants, water carries nutrients from the soil up through the roots and into the leaves, supporting photosynthesis and growth. In animals, water transports oxygen, nutrients, and waste products through the bloodstream, facilitating the countless reactions that keep cells and tissues alive. Water's solvent properties also enable chemical reactions within cells. Biological processes depend on reactions that often occur only in an aqueous, water-based environment. Water molecules can surround charged particles, like ions, which allows them to move freely and react with other substances. Without water's solvent abilities, essential biochemical reactions from energy production to DNA synthesis would grind to a halt. Life's complexity and diversity are possible largely because water acts as a medium in which molecules can move, meet, and interact. No other substance in the universe has quite the same capacity to dissolve such a wide range of compounds while remaining stable across a wide range of conditions. One of the most peculiar properties of water, and one with profound implications for life, is that its solid form is less dense than its liquid form. This is rare for substances, as most become denser when they solidify. In the case of water, however, hydrogen bonds between molecules cause ice to form a crystalline structure that is less dense than liquid water. As a result, ice floats. This may seem trivial, but in reality, it's crucial for sustaining life in aquatic environments. When bodies of water freeze, ice forms on the surface, creating an insulating layer that helps retain the warmth below. This insulation prevents entire lakes, rivers, and even oceans from freezing solid, allowing life to survive in the liquid water beneath the ice. This ability of ice to float and insulate is especially important in colder climates, where lakes and ponds freeze over in winter. Aquatic plants and animals can continue to live in the water under the ice, where temperatures remain relatively stable. If ice were denser than liquid water, it would sink, causing entire bodies of water to freeze from the bottom up. In this alternate scenario, aquatic ecosystems would be destroyed each winter, as few organisms could survive such conditions. The floating ice phenomenon allows life to endure through seasonal changes, preserving biodiversity and enabling the evolution of cold-adapted species. Water's unique properties extend to its role as a medium for biochemical reactions essential to life. Many reactions within living organisms depend on water's molecular structure, specifically its polarity. Water molecules have a slightly positive charge on one end and a slightly negative charge on the other, making them polar. This polarity allows water molecules to form hydrogen bonds with each other and with other polar molecules, giving water its cohesive and adhesive properties. Cohesion allows water to stick to itself, which is why it can form droplets and flow smoothly. Adhesion, on the other hand, allows water to stick to other surfaces, like the walls of plant cells. Together, these properties enable capillary action, the process by which water moves up thin tubes against gravity, which is essential for transporting water in plants and trees. If Earth's primary solvent were anything other than water, life would look drastically different, if it could exist at all. Alternative solvents, like ammonia or methane, do exist in nature and may theoretically support life under extreme conditions, but they lack the versatility and stability of water. For example, ammonia remains liquid only at very low temperatures and is less effective than water at dissolving a broad range of substances. Methane, similarly, is a poor solvent for many of the organic compounds necessary for life as we know it. These substances do not have water's high specific heat or density properties, which means they would not provide the same level of environmental stability that life on Earth relies upon. Without water's unique properties, the carbon-based life forms that thrive on Earth would struggle to survive. Carbon, the backbone of organic chemistry, relies on water's solvent properties to facilitate complex reactions that form the basis of proteins, DNA, and cellular structures. In a world without water, carbon might not interact as readily with other elements, and life's molecular machinery would be vastly different, or potentially non-existent. Even if life could adapt to another solvent, it would likely be simpler and less diverse than the life that exists in Earth's water-based biosphere. Water also plays a key role in Earth's climate regulation. Because of its high specific heat, water acts as a buffer against extreme temperature changes, keeping the planet's climate within a range that supports life. Oceans absorb solar heat during the day and release it slowly over time, moderating temperatures across the globe. This property creates more consistent climates, supporting stable habitats and diverse ecosystems. Without water's ability to stabilize temperatures, Earth would experience more drastic fluctuations, which could make life difficult to sustain. Extremes in temperature would strain organisms, many of which require narrow temperature ranges to survive, and would lead to a more volatile environment overall. The perfect bonding of atoms. At the core of all known life on Earth lies an extraordinary element: carbon. Carbon's unique ability to form stable, complex molecules is the foundation of life's chemistry, making it the essential building block for the biomolecules that constitute living organisms, such as DNA, proteins, carbohydrates, and lipids. This ability comes down to the versatility of carbon's bonding properties, which allow it to create an almost limitless variety of structures. Carbon's special characteristics set it apart from other elements, making it the most favorable for forming the complex, intricate compounds needed for life. If life were based on another element, like silicon, a common hypothetical alternative, its molecular complexity and stability would be severely limited, possibly making life as complex as we know it impossible. One of carbon's most important characteristics is its valency, or bonding capacity. Carbon has 4 electrons in its outer shell and needs 4 more to achieve a stable electron configuration. This allows carbon to form 4 covalent bonds with other atoms, a trait that gives it unmatched flexibility in molecular construction. Carbon atoms can bond with each other in long chains or ring structures, forming the backbone of organic compounds. This bonding versatility enables carbon to create an extensive variety of shapes and structures, from simple molecules like methane, CH4, to highly complex macromolecules like DNA and proteins. This range of bonding possibilities underpins the enormous diversity of organic compounds and allows for the intricate, self-replicating molecules that drive biological processes. Another key aspect of carbon's versatility is its ability to form single, double, and triple bonds. Carbon can bond with other carbon atoms or with atoms of other elements in various ways, creating a vast array of compounds. Single bonds, as in ethane, C2H6, allow for flexible, rotating structures that can adjust to different configurations. Double bonds, as in ethene, C2H4, create planar structures that limit rotation, providing stability and rigidity in certain regions of molecules. Triple bonds, as in acetylene, C2H2, are even stronger and more rigid, offering yet another structural option. The ability to use different types of bonds allows carbon-based molecules to be both stable and reactive, a combination that is essential for life processes. Carbon's bonding strength with other elements is another unique property. The bonds between carbon and other atoms such as hydrogen, oxygen, and nitrogen are strong enough to withstand the moderate temperature ranges on Earth. This stability means that carbon-based molecules don't break apart easily, allowing them to maintain their structure over time, which is essential for the persistence of life. At the same time, these bonds are not so strong that they become inert. Carbon compounds can participate in chemical reactions, breaking and forming new bonds as needed, a property essential for metabolism, growth, and reproduction. This balance between stability and reactivity is rare among elements and is a key reason why carbon is so well suited for the chemistry of life. Carbon's versatility also allows it to form functional groups, small clusters of atoms that attach to carbon chains and give molecules distinct properties. These functional groups, such as hydroxyl, OH, carboxyl, COH, amino, NH2, and phosphate, PO4, are involved in biochemical processes and play a critical role in the structure and function of biomolecules. For example, the amino and carboxyl groups enable the formation of proteins by linking amino acids together in long chains that fold into specific shapes. Proteins, in turn, perform countless functions in living organisms, from catalyzing chemical reactions as enzymes to providing structural support. Without the ability to form functional groups, carbon-based molecules would lack the diversity needed to carry out these complex biological roles. Carbon's bonding properties make it uniquely suited for forming polymers, large molecules made up of repeating units. DNA, for example, is a polymer made up of nucleotide units, each containing a phosphate group, a sugar, and a nitrogenous base. The carbon-based backbone of DNA is both flexible and stable, allowing the molecule to twist into a double helix and maintain its structure over time. DNA's stability ensures the accurate storage of genetic information, while its flexibility allows it to be read and replicated by cellular machinery. Similarly, carbohydrates and proteins, which are also polymers, can adopt various structures to fulfill different functions in cells and organisms. This polymeric capability of carbon is essential for the complexity and diversity of life on Earth. If life were based on another element, such as silicon, it would face significant limitations. Silicon is often cited as a possible alternative to carbon because it also has 4 electrons in its outer shell and can form 4 covalent bonds. However, silicon's bonding properties differ markedly from those of carbon. Silicon-silicon bonds are much weaker than carbon-carbon bonds, making silicon-based structures less stable. Silicon is also larger than carbon, meaning that silicon atoms cannot form the same compact structures as carbon, which limits the variety of shapes and molecules that silicon-based compounds can achieve. Additionally, silicon does not form double and triple bonds as readily as carbon, reducing the structural diversity that is so critical to the complexity of biomolecules. One of the biggest challenges with silicon-based life would be the reactivity of silicon compounds. Silicon readily reacts with oxygen to form silicon dioxide, SiO2, a stable compound commonly found in sand and quartz. Unlike carbon dioxide, CO2, which is a gas that easily diffuses and can be incorporated into biological processes, silicon dioxide is a solid with low solubility in water. This means that a silicon-based organism would struggle to excrete waste products or process energy efficiently. Carbon dioxide, in contrast, is easily released by living organisms through respiration and plays a role in the carbon cycle that regulates atmospheric levels of CO2. Silicon-based life forms would likely be constrained by a lack of similarly efficient waste elimination pathways, which would limit their ability to sustain complex life processes. The biochemistry of silicon also poses challenges. Silicon's reactivity with oxygen leads to compounds that are stable but lack the flexibility needed for metabolic processes. In a hypothetical silicon-based organism, the energy required to break silicon-oxygen bonds would make metabolic reactions inefficient, slowing down the rate at which these organisms could grow, reproduce, and respond to environmental changes. Furthermore, silicon compounds are less soluble in water, which would complicate the transport of nutrients and waste products. Carbon's compatibility with water-based chemistry is a significant advantage, as water serves as the solvent in which nearly all biological reactions take place on Earth. Water itself interacts more effectively with carbon-based compounds than with silicon-based compounds. The polar nature of water molecules allows them to dissolve and transport carbon-based molecules throughout organisms, supporting metabolism, growth, and cellular communication. Silicon compounds, however, are often insoluble or poorly soluble in water, which would make it difficult for silicon-based life to achieve the same level of complexity and interconnectivity found in carbon-based life. Without efficient molecular transport and interaction, the biochemical processes necessary for life would be hindered, limiting the potential for silicon-based organisms to reach high levels of complexity. Carbon's ability to form stable yet reactive molecules with other essential elements, such as hydrogen, oxygen, and nitrogen, allows it to support the rich diversity of chemical reactions that power life. The energy stored in carbon-hydrogen bonds can be released in controlled reactions, such as cellular respiration, providing fuel for life processes. In contrast, silicon-hydrogen bonds are much less stable, making them less suited for sustaining energy-intensive processes. The intricate balance that carbon strikes between stability and reactivity is unique, making it the only known element that can support the complex and dynamic biochemistry required by life. Gravity. Gravity is one of the fundamental forces of the universe, essential for shaping the large-scale structure of matter. Although it is the weakest of the 4 fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, gravity's influence becomes dominant over vast distances. This makes it the primary force responsible for pulling matter together, leading to the formation of stars, planets, and galaxies. Gravity's consistent pull across space has been crucial in creating the stable, organized universe we observe today. Without gravity, or with even a slight change in its strength, the structure of the cosmos, and consequently life itself, would look drastically different if it existed at all. Gravity operates on all matter, attracting particles of dust and gas in the early universe and bringing them together to form clumps. Over time, these clumps grew larger, coalescing to form the first stars and galaxies. When the universe began after the Big Bang, it consisted mainly of hydrogen and helium gas, spread out relatively uniformly. But tiny fluctuations in the density of this gas allowed regions with slightly more matter to pull in neighboring particles through gravitational attraction. These regions gradually became denser, pulling in even more gas, which eventually led to the formation of protostars, the precursors to stars. As gravity continued to pull in gas and dust, protostars eventually reached high enough temperatures and pressures at their cores to trigger nuclear fusion, the process that powers stars. Fusion releases energy, counteracting the inward pull of gravity and preventing the star from collapsing. This balance between gravitational contraction and fusion-generated pressure allowed the first stars to achieve stability, marking the start of the universe's stellar population. These stars produced heavier elements through fusion, which were then released into space when the stars exploded as supernovae. This dispersal of elements seeded the cosmos with the building blocks for planets, life, and complex structures. Gravity's role didn't stop with stars. In the dense regions of gas where multiple stars formed, gravity pulled these stars together to create galaxies. These galaxies clustered to form even larger structures, like galaxy clusters and superclusters. The process continues today, with gravity acting as a cosmic sculptor that brings stars into galaxies and galaxies into clusters. Without gravity, these large-scale structures could never have formed, and the universe would be a homogeneous spread of gas and dust, without any of the organized systems that characterize it today. Gravity is also responsible for planet formation. Around new stars, disks of gas and dust form due to gravitational attraction. These disks slowly coalesce, forming clumps that eventually grow into planets, moons, and other objects in a solar system. The formation of our own solar system followed this process, with the Sun pulling in surrounding gas and dust to form a disk. Over millions of years, clumps of matter in this disk collided and merged, eventually forming the planets, including Earth. Gravity's pull allowed Earth to maintain a stable orbit around the Sun, creating the predictable conditions necessary for life to evolve. If the strength of gravity were altered, the universe would look vastly different. Even a slight increase in gravitational strength would lead to a rapid collapse of matter. Stars would form faster, but they would also burn through their nuclear fuel more quickly, leading to shorter lifespans. Massive stars would collapse under their own gravity at much earlier stages, potentially resulting in a universe dominated by black holes rather than stable stars. The delicate balance of gravity and fusion that sustains stars like our Sun would be disrupted, as increased gravitational force would require greater pressure to resist collapse, causing stars to burn hotter and faster. In such a universe, stars would be short-lived, leaving little time for planets to form or life to evolve. A universe with stronger gravity would also see rapid galaxy formation, but these galaxies might collapse back on themselves due to the overwhelming gravitational pull. Large-scale structures, such as galaxy clusters, might form faster and be denser, but this could lead to instability. Supermassive black holes would dominate the centers of these galaxies, and their gravitational pull would prevent the formation of stable solar systems. Planets orbiting stars in these dense environments would be subject to extreme gravitational forces, causing chaotic orbits and rendering stable, life-supporting conditions unlikely. Conversely, a weaker gravitational force would create a universe lacking in the structure we observe today. If gravity were significantly weaker, the initial clumps of gas in the early universe would have been unable to collapse to form stars. Without the gravitational pull necessary to overcome the pressure within gas clouds, stars simply wouldn't ignite, leaving the universe dark and empty. The formation of galaxies and planetary systems would be impossible, as matter would remain too diffuse to come together in meaningful ways. In this scenario, there would be no planets, no stars, and no life. matter would be spread thinly across space, floating as isolated particles or small clouds of gas with no potential for evolution. A weaker gravity would also prevent the formation of stable orbits. For instance, planets like Earth rely on the gravitational pull of their stars to maintain consistent orbits. These orbits create the stability needed for life to develop by ensuring a regular climate and seasonal changes. In a universe with weaker gravity, planets would either drift away from their stars or be unable to form at all. The intricate gravitational dance that keeps Earth at a life-sustaining distance from the Sun would be impossible. Additionally, moons, which play essential roles in stabilizing planetary tilts and influencing climates, as Earth's moon does, would not form in a universe with weaker gravity, or if they did, they would be easily lost. Gravity's role extends beyond mere structural formation. It also affects time itself. According to Einstein's theory of general relativity, gravity influences the flow of time, causing it to slow down in regions of strong gravitational fields. This phenomenon, known as gravitational time dilation, means that time moves slightly slower on Earth's surface than it does in outer space, where gravity is weaker. While this effect is minuscule for most day-to-day purposes, it becomes significant in the realm of astrophysics and cosmology. Time dilation near massive objects like black holes would be extreme, leading to conditions where time nearly stops at the event horizon. In this sense, gravity not only structures the universe, but also shapes the nature of space and time. In addition to creating structure, gravity also plays a role in cosmic evolution. Galaxies collide and merge due to gravitational attraction, leading to the growth of massive galaxies over billions of years. Our own Milky Way, for example, has undergone numerous mergers, each event shaping its structure and triggering waves of star formation. The gravitational forces between galaxies drive this process, pulling galaxies together and leading to a constantly changing universe. Without gravity, galaxies would not interact, merge, or grow, resulting in a far simpler and less dynamic cosmos. Gravity is also essential for maintaining life-supporting conditions on planets like Earth. Gravity holds Earth's atmosphere close to the surface, creating the conditions necessary for breathing, weather patterns, and climate stability. The force of gravity ensures that water and other essential resources remain on the planet's surface, providing an environment where life can flourish. It also enables Earth's oceans to remain in place, which are crucial for regulating climate and supporting ecosystems. A planet without sufficient gravity would struggle to hold on to its atmosphere, leading to conditions similar to Mars, where a weak gravitational field allowed much of its early atmosphere to escape into space, the heart of stars. At the core of every star lies a powerful engine of energy production, nuclear fusion. Fusion in stellar cores is the process by which atoms of hydrogen, the simplest and most abundant element in the universe, are fused together to form helium. This process releases vast amounts of energy, which radiates out from the core and provides the light and warmth that can reach planets orbiting the star. Fusion is what keeps stars shining, and it is this steady energy output that supports the conditions necessary for life on nearby planets, such as Earth. Without fusion, stars would not exist as we know them, and the universe would be a dark, cold place. In stars like our Sun, nuclear fusion begins with hydrogen atoms, each consisting of one proton and one electron. In the extreme conditions at the core of a star, where temperatures reach around 15 million degrees Celsius, 27 million degrees Fahrenheit, and pressures are unimaginably high, hydrogen atoms are stripped of their electrons and become positively charged protons. These protons, under normal conditions, would repel each other due to their like charges, but in the star's core, the intense pressure and temperature push them close enough together that the strong nuclear force, one of the four fundamental forces, takes over, allowing them to overcome their repulsion and fuse. This fusion process releases energy because of Einstein's famous equation, E = mc2, which tells us that mass can be converted into energy. When hydrogen nuclei fuse to form helium, a tiny fraction of the mass is lost in the process, converted into energy that powers the star. For each fusion reaction, an enormous amount of energy is released, and in the Sun, these reactions happen continuously in astronomical numbers every second. The energy generated in the core gradually makes its way outwards, passing through different layers of the star until it finally escapes into space as light and heat. This radiation provides the warmth necessary for life on Earth and the light that allows plants to photosynthesize, forming the base of the food chain. The energy from fusion also creates outward pressure that balances the inward pull of gravity. Gravity constantly tries to collapse the star inwards, and without fusion's counteracting pressure, the star would eventually collapse under its own weight. Fusion acts as a stabilizing force, ensuring that stars maintain their size and structure. This balance between gravity and fusion pressure is known as hydrostatic equilibrium and is essential for a star's stability. If this equilibrium is disturbed, the star may undergo dramatic changes, potentially leading to expansion into a red giant or collapsing into a white dwarf, neutron star, or black hole, depending on its mass. The light and energy produced by fusion define the habitable zone around a star, which is the region where conditions are just right for liquid water to exist on a planet's surface. For planets in this zone, like Earth, the energy from the star provides a stable climate that can support life. In our solar system, the habitable zone lies between the orbits of Venus and Mars, with Earth positioned at an optimal distance from the Sun to receive enough warmth without overheating. If the Sun produced less energy, this habitable zone would shrink, pushing it closer to the star. Planets like Earth, which currently enjoy life-supporting conditions, would become too cold, with temperatures dropping to levels that would likely freeze water and make life as we know it impossible. Now, consider if fusion were less efficient. In such a scenario, stars would produce less energy from the fusion process, leading to dimmer, cooler stars. The habitable zone around these stars would be much narrower and closer to the star itself, reducing the space within which planets could exist with stable, life-supporting conditions. Dimmer stars would struggle to provide enough warmth to sustain liquid water on planets orbiting at Earth-like distances, drastically limiting the potential for life. Less efficient fusion would also mean that stars would burn through their hydrogen fuel more slowly, resulting in longer lifespans but less energy output. While this might seem beneficial, it would lead to different planetary climates than those we see in our solar system. Planets around these stars would need to orbit closer to maintain temperatures suitable for life, which would make them vulnerable to stellar flares and radiation from their star's surface. This proximity could also mean that planets would become tidally locked to their star, with one side constantly facing the star while the other remains in perpetual darkness. Such conditions would create extreme temperature differences between the two sides, posing additional challenges for life to develop and thrive. Stars with less efficient fusion would likely have reduced stellar wind as well, affecting the formation of planets and planetary atmospheres. Stellar winds, streams of charged particles emitted from a star, play an important role in shaping and stabilizing planetary atmospheres. For instance, the Sun's stellar wind helps to shield Earth from cosmic rays, while also influencing the orbits of smaller bodies in the solar system. If fusion were less efficient, these winds would be weaker, potentially leaving planets more exposed to cosmic radiation, which could strip away atmospheres over time and make conditions more hostile. Conversely, if fusion were too efficient, stars would produce much more energy, leading to intense luminosity and heat. This would push the habitable zone farther out, making it difficult for planets closer to the star to maintain the conditions necessary for life. Stars with highly efficient fusion would also have shorter lifespans, as they would burn through their fuel more quickly. Massive stars, which already have short lifespans, would become even shorter-lived, potentially exploding as supernova before life had time to evolve on any nearby planets. Such a universe would be populated with stars that burn brightly but briefly, leaving less time for stable, habitable conditions to develop around them. The efficiency of fusion not only affects stars individually, but also plays a role in the overall evolution of galaxies and the distribution of elements in the universe. When stars undergo fusion, they produce heavier elements such as carbon, nitrogen, and oxygen, which are necessary for life and are spread into the interstellar medium when stars explode as supernovae. If fusion were less efficient, these elements would be produced at a slower rate, meaning that the universe would be less enriched with the ingredients for life. Planets forming in such a universe might lack the essential elements needed for complex chemistry, making life less likely. Fusion's role as the engine of stars is not just about energy production. It is about creating the conditions for chemical complexity. Without fusion, there would be no continuous production of the heavier elements that make up planets, water, and biological molecules. The carbon, nitrogen, and oxygen atoms that form the backbone of organic molecules are all produced in stars through fusion. The most massive stars, after exhausting their hydrogen fuel, go on to fuse helium into carbon, oxygen, and other elements, enriching the cosmos with the raw materials of life. When these stars reach the end of their lives, they release these elements into space, where they can become part of new stars and planets, enabling the cycle of life to continue. The strong nuclear force, binding the universe's core. The strong nuclear force is one of the most fundamental forces in the universe, and yet it is perhaps the least familiar to most people. It operates at the atomic level, binding protons and neutrons together in the nucleus of atoms, creating the essential stability required for matter to exist. Without this force, the universe as we know it would be an entirely different place, devoid of the stable atoms that make up everything from stars and planets to the molecules in our bodies. This force is incredibly powerful over very short distances, about the diameter of an atomic nucleus, but it quickly diminishes beyond that range. It is this precise, delicate balance that enables the strong nuclear force to perform its essential role in creating and sustaining the building blocks of matter. In every atomic nucleus, protons and neutrons are packed together in close quarters. Protons carry a positive charge, meaning they naturally repel each other due to electromagnetic force. Similar charges push each other away. The strong nuclear force overcomes this repulsive force by binding protons tightly to neutrons within the nucleus. Acting only over extremely short distances, the strong force essentially glues the particles together, allowing protons and neutrons to coexist within a stable nucleus. Neutrons, which are neutral in charge, play a stabilizing role, offsetting the intense repulsion between positively charged protons by mediating the strong force within the nucleus. The strength of the strong nuclear force is both remarkable and finely tuned. It must be strong enough to hold the protons and neutrons together within the nucleus, but not so strong that it binds them too tightly. If the strong nuclear force was slightly weaker, the nuclei of atoms would not hold together, and stable atoms could not form. Without stable nuclei, elements as we know them would not exist, and the universe would be made up of a sparse mix of fundamental particles with no structure or complexity. This fine balance of strength is essential for the existence of atoms, which are the basic units of matter. This balance also allows for the creation of heavier elements through processes in stars. Within stars, nuclear fusion combines lighter elements, such as hydrogen, to form heavier elements like helium, carbon, and oxygen. During fusion, the strong nuclear force holds the newly formed nuclei together, stabilizing these heavier elements. Without the strong force to bind these elements, the universe would consist only of the lightest particles, with no chance of forming the complex elements that are necessary for life. The process of fusion also releases vast amounts of energy, powering stars, and, by extension, creating the light and heat necessary for habitable conditions on nearby planets. If the strong nuclear force were slightly stronger, atomic nuclei would be bound too tightly. A stronger force would make it difficult for atoms to participate in nuclear reactions, as it would require more energy to separate protons and neutrons from each other. Stars, for instance, rely on fusion reactions, where atomic nuclei combine to form heavier elements and release energy. If the strong force were too strong, fusion reactions would be less efficient, and stars would struggle to produce the energy necessary for their stability and to sustain life on planets in their orbit. A stronger force would also limit the diversity of elements in the universe. During stellar nucleosynthesis, stars create a range of elements by fusing lighter ones, but if atomic nuclei were too tightly bound, only a few types of elements could form. The heavier elements, such as carbon, nitrogen, and oxygen, which are essential for life, might not be produced in abundance. This lack of elemental variety would make it difficult for complex molecules to form, which in turn would limit the possibilities for life to develop. The intricate chemistry that defines life on Earth depends on a wide range of elements and stable isotopes, all of which rely on the precise strength of the strong nuclear force. Conversely, if the strong nuclear force were weaker, atoms would lack the stability necessary for their existence. A weaker strong force would fail to counteract the repulsive electromagnetic force between protons in the nucleus, causing atomic nuclei to break apart. In this scenario, protons and neutrons would be unable to bind together, and atoms could not form at all. The universe would consist of a chaotic sea of fundamental particles without structure, with no atoms, no molecules, and no chance for stars, planets, or life to emerge. Matter, as we know it, would simply not exist. Even the smallest change in the strength of the strong nuclear force would drastically alter the types and properties of atoms that could form. Atomic stability is highly sensitive to this force. In the actual universe, most of the atomic nuclei are stable enough to exist without breaking apart, allowing for the formation of complex molecules and chemical reactions. A slightly weaker force would render many of these nuclei unstable, causing them to decay almost immediately. This would eliminate the possibility of stable elements like carbon, hydrogen, and oxygen, which are essential for life. The stability of isotopes also depends on the strong nuclear force. Isotopes are atoms of the same element with different numbers of neutrons. Some isotopes are stable, while others are radioactive and decay over time. The balance of the strong nuclear force is critical for determining this stability. If the force was stronger or weaker, the range of stable isotopes would narrow significantly, potentially excluding some isotopes that are vital for biological processes. For instance, carbon-12 and carbon-14 are isotopes of carbon with slightly different numbers of neutrons. Carbon-14 is radioactive and is used in radiocarbon dating, an important tool in archaeology and paleontology. If the strong nuclear force were different, carbon-14 might not exist, or its stability could be altered, removing this invaluable dating method. The formation of complex atomic structures also depends on the strong nuclear force. The intricate shapes and interactions of atoms in biological molecules, from DNA to proteins, rely on stable elements with specific atomic properties. This stability enables atoms to form complex molecules, with bonds that are strong enough to withstand biochemical processes, but flexible enough to participate in reactions essential for life. If the strong nuclear force were too strong, atomic bonds might become rigid, limiting the flexibility needed for these reactions. Conversely, a weaker force would make atomic bonds too fragile, causing complex molecules to break down easily. In either case, life's molecular machinery would be impossible to sustain, as the chemistry of living organisms requires a precise balance between strength and flexibility. In stars, the delicate balance of the strong nuclear force enables stellar nucleosynthesis, the process by which elements are forged in the intense heat and pressure of stellar cores. This process relies on the ability of atomic nuclei to fuse together, releasing energy and creating new elements. If the strong force were slightly weaker or stronger, this balance would be disrupted, and stars would fail to produce the heavier elements essential for planets, water, and organic molecules. Stellar nucleosynthesis is responsible for creating all elements heavier than hydrogen, so any change in the strong force would result in a universe lacking these elements, severely limiting the potential for complex matter and life. The fine-tuning of physical constants. The universe as we know it operates according to a set of fundamental physical constants that govern the behavior of matter and energy. These constants include the speed of light, c, Planck's constant, h, and the gravitational constant, g, among others. Together, they form the backbone of the laws of physics, dictating everything from the structure of atoms to the formation of galaxies. What's remarkable about these constants is their precise values. If they were even slightly different, the universe would be a vastly different place, likely one incapable of supporting life. The concept of fine-tuning refers to how delicately balanced these constants are, making our universe uniquely suitable for complex structures and living organisms. One of the most famous constants is the speed of light, symbolized by c, which is approximately 299,792 kilometers per second. The speed of light plays a central role in the laws of physics, particularly in Einstein's theory of relativity. It is the maximum speed at which information or matter can travel, and it serves as a fundamental limit in the universe. Light speed governs how quickly we observe events occurring at a distance and sets the scale for cause and effect relationships across space. If the speed of light were significantly different, it would affect the structure of space and time itself. A slower speed of light would change how we perceive distances, and it would alter the dynamics of energy and mass, likely leading to a different structure of galaxies, stars, and even atoms. If the speed of light were faster, it might affect causality, potentially allowing particles to influence each other instantaneously across vast distances, disrupting the orderly progression of cause and effect that we observe in our universe. This alteration would make it difficult for stable structures, like atoms and galaxies, to form and persist. Furthermore, the speed of light is tightly coupled with other constants, such as Planck's constant, which governs quantum mechanics. Any alteration in c would ripple through the laws of physics, reshaping the entire fabric of the universe. Another fundamental constant is Planck's constant, h, which is essential to quantum mechanics. Planck's constant determines the scale of quantum effects, which dictate the behavior of particles on the smallest scales. Quantum mechanics relies on the concept that energy, momentum, and other properties are quantized, meaning they exist in discrete units rather than continuous values. Planck's constant sets the size of these units, essentially defining the granularity of the universe at the quantum level. If Planck's constant were even slightly different, it would affect the stability of atoms, the behavior of chemical reactions, and the formation of molecules. For example, if Planck's constant were larger, quantum uncertainty would increase, making it harder for electrons to stay bound within atoms. Atoms might become unstable, breaking apart before they could form the molecules necessary for life. Conversely, if Planck's constant was smaller, quantum effects would be minimized, making the universe more deterministic. The lack of quantum randomness could prevent the formation of complex molecules and the chemistry required for life. The precise value of Planck's constant allows for a balance between stability and flexibility, creating the conditions for complex chemistry and ultimately for life. The gravitational constant, g, is another key component of our universe's structure, setting the strength of gravity, the force that pulls matter together and shapes galaxies, stars, and planets. Gravity operates on all matter, attracting it over vast distances and driving the formation of cosmic structures. If g were even slightly different, the universe would either collapse in on itself or be too diffuse for stars and galaxies to form. A stronger gravitational constant would cause matter to clump together too quickly, leading to a rapid collapse of the universe shortly after the Big Bang. Stars would form but burn out quickly, and black holes might dominate, making stable planetary systems unlikely. On the other hand, if the gravitational constant were weaker, matter would struggle to come together. leading to a sparse and fragmented universe. Stars and galaxies might never form at all, as the gravitational pull would be too weak to overcome the expansion of the universe. Without stars, there would be no light, no heat, and no sources of the heavy elements needed for life. A weaker gravitational force would also impact the stability of planets. Any planets that did form would be unlikely to maintain stable orbits, making conditions inhospitable for life. The fine-tuning of these constants becomes even more evident when we consider how they work together to maintain the universe's structure. For example, the gravitational constant, g, and the electromagnetic force constant are both crucial in determining how matter behaves on different scales. While gravity is the dominant force over vast distances, the electromagnetic force is much stronger at short ranges, governing the interactions between charged particles, including those within atoms. The balance between these two forces is critical. If the electromagnetic force were even slightly stronger relative to gravity, stars might not be able to form because the repulsive forces between particles would prevent matter from collapsing under gravity. The electromagnetic force constant, in particular, is essential for chemical bonding. It determines the strength of the forces between protons and electrons, allowing atoms to form and interact in stable ways. If this constant were weaker, electrons might not be held tightly enough to atomic nuclei, making it difficult for atoms to exist in their stable forms. Molecules, which are built from interactions between atoms, would have limited structures, preventing the diversity of chemical compounds that are necessary for life. Conversely, a stronger electromagnetic force constant would pull electrons too close to the nucleus, reducing the potential for chemical bonding and resulting in a universe without the rich chemistry needed to support complex life. Another fascinating aspect of fine-tuning is seen in the cosmological constant, lambda, which relates to the expansion rate of the universe. The cosmological constant acts as a counterforce to gravity, causing the universe's expansion to accelerate. If this constant were even slightly larger, the universe would expand so rapidly that galaxies, stars, and planets would not have time to form. A smaller cosmological constant would lead to a slower expansion, potentially causing the universe to collapse back in on itself in a big crunch. The precise value of the cosmological constant allows for a universe that expands just fast enough to form stable cosmic structures, but not so fast that they are torn apart. The ratio between the strong and weak nuclear forces is also finely tuned. The strong nuclear force holds atomic nuclei together, while the weak nuclear force plays a role in nuclear reactions, including those in stars. If the strong force was slightly weaker, atomic nuclei would not be stable, and atoms as we know them could not exist. If it were stronger, nuclei might be too tightly bound, preventing nuclear reactions like fusion. Fusion is essential in stars, producing the energy that supports life on planets and creating the elements that make up everything from water to organic compounds. Together, these constants create a universe that is both stable and dynamic, allowing for the formation of galaxies, stars, planets, and the chemical elements necessary for life. The precise values of these constants enable conditions that support complex chemistry, structured matter, and energy processes critical for life. If even one of these constants were altered, it would ripple through the laws of physics, unraveling the delicate balance that defines the cosmos. Supernova explosions. Supernova explosions are among the most powerful and spectacular events in the universe, marking the dramatic end of a star's life cycle. These cataclysmic detonations are not only awe-inspiring celestial spectacles, but also vital processes that contribute to the creation and distribution of heavy elements throughout the cosmos. During a supernova, a massive star exhausts its nuclear fuel, leading to a catastrophic collapse under its own gravity, followed by a rebound explosion that ejects the star's outer layers into space. This explosion is responsible for forging and dispersing essential elements like carbon, oxygen, and iron, elements that are crucial for the formation of rocky planets and the biological structures necessary for life. In the life of a massive star, the process of nuclear fusion creates increasingly heavier elements as the star ages. Initially, hydrogen nuclei, protons, fuse to form helium. As the star evolves, it can reach temperatures and pressures high enough to allow for the fusion of helium into heavier elements like carbon and oxygen. This process continues, with stars forming progressively heavier elements, culminating in the production of iron in their cores. Iron is the end product of fusion because it is the most stable nucleus and cannot release energy through fusion any longer. Once the core of the star is primarily iron, it becomes unable to support the star against gravitational collapse, setting the stage for a supernova explosion. When a star goes supernova, the immense energy released during the explosion enables the production of elements heavier than iron through a process known as neutron capture. In the intense environment of a supernova, neutrons are abundant and they can be captured by atomic nuclei, leading to the formation of elements like nickel, copper, and even uranium. These newly created elements are expelled into the surrounding interstellar medium during the explosion, enriching the space around the star with essential materials. This process contributes to the cosmic abundance of elements, ensuring that they are available for the formation of new stars, planets, and ultimately life. The dispersal of these elements is crucial for the formation of rocky planets like Earth. After a supernova, the heavy elements produced are mixed into the gas and dust of the interstellar medium, where they can become part of new stars and planetary systems. As gravity pulls together gas and dust, these materials coalesce to form new stars and planets, with the heavier elements providing the building blocks for rocky worlds. Without the carbon, oxygen, and iron generated in supernovae, the formation of terrestrial planets would be unlikely, as these elements are necessary for creating the minerals and compounds that make up rocks and soils. Carbon, for instance, is a fundamental building block of life, forming the backbone of organic molecules like carbohydrates, proteins, and nucleic acids. Oxygen is essential for respiration in many life forms and plays a vital role in the formation of water, which is crucial for life. Iron is key for various biological processes, including oxygen transport in blood. These elements are not only vital for individual organisms, but also for the development of ecosystems and the complex interactions that sustain life. Now imagine a universe without supernovae. In this scenario, the production and distribution of heavy elements would be severely limited. Without the explosive deaths of massive stars, there would be no mechanism to create elements beyond helium in significant quantities. The universe would be predominantly composed of hydrogen and helium, the lightest elements formed during the Big Bang. While hydrogen and helium can form stars and simple molecules, the absence of heavier elements would prevent the creation of rocky planets and complex chemistry necessary for life. In such a universe, planets would either remain as gaseous giants, similar to the gas giants we find in our solar system, or they would form primarily from lighter elements, resulting in icy or gaseous bodies without the necessary rocky components. The lack of carbon, oxygen, and other heavy elements would also mean that the conditions for life as we know it would be absent. Without the essential elements needed to form organic molecules, complex life forms could not evolve. The universe would lack biodiversity, ecosystems, and the intricate web of life that defines Earth. The absence of supernova would also impact the chemical evolution of the universe. Supernova explosions contribute to the recycling of materials in space, allowing for the ongoing synthesis of new elements and the continuous evolution of stars and planets. In a universe devoid of supernovae, the cosmic material would stagnate, with limited opportunities for new stars and planets to form. The recycling process that enriches the universe with heavy elements would be interrupted, leading to a less dynamic and diverse cosmic landscape. Moreover, the scarcity of heavy elements would hinder the development of more complex chemical processes. Life on Earth depends not only on the presence of essential elements, but also on the variety of chemical reactions that those elements can undergo. A universe without supernovae would likely result in a simpler chemical environment, where the reactions that drive biological processes would be limited. The ability to form complex molecules, such as DNA, proteins, and carbohydrates, would be greatly diminished, leading to a stagnant biochemical landscape. Even in terms of star formation, the absence of supernovae would disrupt the cosmic cycle of birth and death that characterizes the universe. Supernova explosions play a crucial role in triggering the formation of new stars. When a massive star explodes, the shockwave from the supernova can compress nearby gas and dust, igniting new star formation in regions that might have otherwise remained dormant. Without this catalyst, the interstellar medium would lack the disturbances needed to form new stars, leading to a slower pace of stellar evolution. Seeds of structure in the universe. The origins of cosmic structure trace back to the very moments following the Big Bang, a time when the universe was a hot, dense soup of particles. In those earliest moments, quantum fluctuations, tiny, random variations in energy levels at the quantum level, occurred throughout the universe. These fluctuations are believed to have seeded the very fabric of space with density variations, which would grow over billions of years to become the galaxies, stars, and planets we see today. Understanding how these fluctuations contributed to the structure of the universe is key to unraveling the complex tapestry of cosmic evolution. In the immediate aftermath of the Big Bang, the universe was nearly uniform, filled with hot plasma consisting of protons, neutrons, electrons, and photons. However, due to quantum mechanics, small fluctuations in density existed throughout this primordial plasma. These fluctuations are not easily observable on their own, but become significant as the universe expands and cools. As regions of slightly higher density began to form, they created gravitational wells that attracted more matter. Over time, these wells deepened, and the gravitational pull became strong enough to draw in additional gas and dark matter, which further amplified the density fluctuations. This process is critical for the formation of large-scale structures in the universe. As the universe expanded and cooled, it transitioned into the recombination era around 380,000 years after the Big Bang, when electrons combined with protons to form neutral hydrogen atoms. This allowed photons to travel freely, leading to the release of the cosmic microwave background, CMB, radiation. This relic radiation is a snapshot of the universe at that time and exhibits slight temperature fluctuations, which correspond to the density variations seeded by the earlier quantum fluctuations. These tiny variations, mapped in the CMB, are crucial indicators of how the structure of the universe would develop. Areas of slightly higher density in the early universe eventually became the gravitational centers for the formation of galaxies and galaxy clusters. Over billions of years, as gravity acted on these density fluctuations, matter continued to accumulate, forming the first stars. These stars, in turn, created heavier elements through nuclear fusion, enriching the interstellar medium. When massive stars reached the end of their life cycles, they exploded in supernovae, dispersing these newly formed elements into space. The enriched material contributed to the formation of new stars and planetary systems, a process that repeats over cosmic timescales, leading to the diverse structures we observe today. The importance of these quantum fluctuations cannot be overstated. They acted as the seeds from which all cosmic structure would grow. However, the balance of these fluctuations is critical to the formation of stable structures. If there were too few fluctuations, the universe would smooth out, lacking the density variations necessary for gravitational collapse. In this scenario, there would be no stars, no galaxies, and no planets. The universe would remain a homogeneous mix of particles, unable to coalesce into the complex structures that define it. On the other hand, if there were too many fluctuations, the universe would become chaotic. Excessive density variations could lead to rapid gravitational collapses and fragmentation, preventing the formation of stable galaxies and solar systems. Such a chaotic environment would hinder the delicate balance necessary for planets to form and maintain stable orbits around stars. The universe might become a wild place filled with rogue planets and stars, unable to develop the organized structures that can sustain life. The just right amount of fluctuations is reminiscent of the concept of the Goldilocks zone, where conditions are not too extreme but just right for the development of stable systems. This delicate balance is crucial for the creation of galaxies and star systems that can host planets. The presence of dark matter, which interacts gravitationally but not electromagnetically, also plays a role in this process. Dark matter provides additional gravitational pull without forming structures of its own, helping to amplify the density fluctuations and facilitate the formation of galaxies. As cosmic structure continues to evolve, the original quantum fluctuations set in motion a series of events that contribute to the richness and diversity of the universe. Each new generation of stars contributes to the ongoing cycle of cosmic evolution, forging heavier elements and recycling materials into new stars, planets, and potentially life. This continuous interplay between gravity, quantum mechanics, and the structure of the universe underpins the dynamic and ever-changing cosmos. I hope you enjoyed the video. If you did, feel free to subscribe to the channel. Thanks for watching.